30 volts DC, free energy that's not affecting the light at all. So check this out. I just have the two 6.6 watt LED light bulbs hooked up, just the two, and then I'm gonna plug in the 40 watt. And look what happens to the voltage on the pickup coil. Watch this. I'm gonna plug this in. It starts singing too. 2 volts. The 32 volts. I'm gonna plug that in, and then the light bulbs stay on. They stop blinking. So it's like the system kind of stabilized a little bit. So what I'm doing here is I'm showing you the difference in waveform on the battery's positive terminal compared to when the system is being fed that secondary energy compared to when it's not. So we're looking at the two different waveforms, and you'll notice when it's not being fed that energy, there isn't as big of a like radiant spike on the negative. But once I hook up that secondary coil to the battery, the positive terminal shows a more negative radiant spike, which is very cool. It's exactly what we want to see. It's not a lot, but it's there, and it's noticeable compared to when it's not. You know, it's something to do with the 0.6 watt efficiency of the bulb, and I suspect because the lights blink on and off, it's trying to simulate a candle, really. I think that's what the light bulb does, is try to simulate the natural flicker of a candle, which it does really well. It's beautiful. But I think the on and off function of the light bulb itself, the LEDs, plays into why this is so efficient, right? And as you'll see immediately, we start charging up.
In the shadows of capitalism's dark secrets, join us on a thrilling new show. Get ready to be inspired, enraged, and empowered as we delve into the Benefactor's Guide to Free Energy Devices.
Only on Beneficence TV.
Welcome back, everybody, to another electrifying episode of the Benefactor's Guide to Free Energy Devices. A show where we dive into the cutting edge, the unexplained, and the outright revolutionary in the world of alternative energy. As you all know, I'm your host, the Benefactor, the disseminator of all things forbidden. Today's episode is a big one. An exciting breakthrough with the lightning thief, some mind-bending resonance phenomena, and a deeper look into how we might be closing the loop on energy recycling in our system. The lightning thief is a device that's redefining what we thought possible with off-the-grid energy management. If you love the unexpected breakthroughs, wild voltage spikes, and light bulbs that sing to you, then buckle up, because this one's going to be one wild ride. Alright, so let's start with a lightning thief refresher. Let's take a quick refresher. For those tuning in for the first time, or if you just need a refresher, the lightning thief isn't some gadget for stealing Zeus's thunderbolts. No. Though it sure feels like we're harnessing a bit of divine power here. At its core, it's a highly efficient energy management system designed to stretch a battery's output to near mythical levels. Instead of a traditional power inverter, which chews up energy with massive losses, the lightning thief takes a different approach. Using high-frequency pulsing, resonance tuning, and back EMF capture, it maximizes the usable energy from a standard battery. Specifically, we're using a 12-volt, 20-amp-hour battery. So by working with the natural oscillations of the system, it steps up voltage while maintaining or even reducing current draw on the battery. Think of it like surfing a wave rather than fighting against the ocean. The lightning thief is a modified joule thief circuit designed to maximize energy extraction from high voltage, low current sources. Its core principle is taking advantage of radiant energy effects and back EMF to drive loads more efficiently than traditional circuits. The backbone of the setup that I'm using currently is the Mark 1 APA coil that you can see behind me. The one that I'm holding, the green one. So this is our primary coil. A toroidal coil wound, and there's another toroidal coil that is the Christmas coil that it is sitting on top of. That's our secondary coil for the system. So what makes this coil unique, the Christmas coil, is that it's actually missing an entire loop around the torus. Yet it still performs remarkably well with picking up this radiant energy. The Mark 1 is driven by high-frequency pulsed DC system, creating strong inductive effects in the secondary Christmas coil. All right, so connected to Mark 1, the green coil, sitting on top of the Christmas coil, the secondary coil, connected to Mark 1, we have a lightning thief circuit, which acts as the first stage of energy processing, stepping up the voltage while maintaining a relatively stable current. The load configurations have varied from 40-watt LED panel to a much smaller 0.6-watt LED light bulb. Specifically that one, which has proven to be a game changer, and we'll get into that in a few minutes. So as you can see here, we have the lightning thief on the right. We have two of them with a little micro vortex coil sitting on top right here. And then to the left of that, we have the lumen lamp. And we'll show you some more of the lumen lamp later. So this is just another picture of the glow-in-the-dark case that I printed out for the lightning thief. Something new and exciting. I think it's going to be very, very cool when I get the finished one. As you can see, this one's kind of jacked up. The printer was messed up. And right now, my 3D printer isn't actually working at all. The thermostat, I don't know what it's called, the thermostat or the sensor for the bed is not working. So we have to replace that. So this is the lightning thief right here. And you can see Ian's cap bank to the left. All right, so the resonance relay in the singing bulb. So now here's where things get a little wild. Let me put because I have pictures up that I forgot to include in here. Let me put them up here for you, just to show you the resonance relay. Give me one moment and I'll load it up. Don't think I had it downloaded off of my drive. Okay, here we go. So I'm going to paste this in the screenshot section. There we go. I have to put it at the bottom. Ooh, that's not a very good copy. There we go. All right, I hope you guys can see that. Let me double check. Yes. All right, so that's the resonance relay. I have also encapsulated it in heat shrink insulation. So I'll show you that as well. I'll be including these with all the prototypes that I'll be sending out. Let's see that. So that is the resonance relay. And here's where things get really wild. This resonance relay is very simple. It's basically a high-speed diode attached to it in an extension wire, a jumper cable. but it was able to double the brightness of the 40-watt LED panel without affecting the current draw. In fact, it might have even slightly reduced it. That's a clue that we're dealing with some kind of energy recycling effect here. But here's the real showstopper. Switching the load from the 40-watt panel to the 0.6-watt LED bulb introduced an entirely new phenomenon. The system stabilized at 10 milliamp draw all around. So we have 10 milliamps coming from the battery now. Instead of like wasting all of that milliamperage, it seems that we're getting 10 milliamps out of the battery, then into the coil, then out of the coil, and then out of the Joule Thief circuit into the light bulb. So with maybe only one milliamp loss. So from the battery to the coil output, and then from the Lightning Thief output, it's all in perfect harmony with that 10 milliamp registering on the multimeter. And then the light bulb started to sing. So this is really interesting. The light bulb started to sing. I've never had that happen with a load before. Nathan suggested that we experiment with a switch on the negative load wire. Why? Because once the bulb starts humming, and then you unplug the negative load wire, we actually increase the efficiency, and it stops the hum. So this is indicating that the system is reaching a state of full resonance. My working hypothesis, based on what Nathan had suggested and Michelle had suggested, is that the coil is saturated with radiant energy when it's humming. And when the negative is disconnected, that energy gets dumped into the load, almost like a capacitor discharging. Only not like all at once. It seems to be slowly discharging as needed, which is very cool, because you just have to unplug it and it just increases the efficiency all around. We're going to play a video of Michelle's diode secret. Give me 1 second to load it up. We have 125 milliamps, and look how dimly lit that is. That's not with the diode. So we have 125 milliamps coming out of the battery. Now we hook up the diode. Set down the phone for a second. I might give myself a minute. Alright, the diode is hooked up. There I go. And look at it goes down to 40 milliamps. And it gets way brighter. Look at that. So about 7 to 8 milliamps. Sometimes it goes up to 10, depending on the position of the meter. See it kind of goes up and down. Meter's not exactly accurate. Might not be the meter either. It might go up and down. But in general, we get about 7 to 10 milliamps coming out. This right back up again. And that is without the diode. Took the diode out now. Yeah, see how low it is? Look how weak that is in comparison. And of course, I don't know about you guys, but if you're watching right now, now's the time to hit the like button, because that is very, very cool. We doubled the brightness and reduced the current draw on the system. That's extraordinary. just by hooking up the resonance relay extension wire. And just so everybody is on the same page, all the stuff that I invent or that the team invents is all in the public domain. We don't have any patents here. It's all CC0. So it's all in the public domain. You can't patent it. We want people to be able to do what they want with it, you know, develop it into something that works for you. So that's really cool. That was the first major breakthrough that we had last week. And then we had some interesting developments with the dual thief setup. And if you're not aware what the dual thief is, it's utilizing two lightning thieves, one with each their own coil. So I'll be using the Mark I coil as the primary driver hooked up to the battery with one lightning thief. And then the Christmas coil, which is sitting below it, the Mark I, it's a little bit bigger than the Mark I, so it's sitting below the Mark I, but they're sitting on top of each other. And the Christmas coil below it is the pickup coil, utilizing another lightning thief circuit, but it's not hooked up to the battery at all. This is just picking up free energy from the wireless induction going on with the primary coil. And you can tell because it's lighting light bulbs and doing stuff without affecting the main circuit lighting. Not really, at least. So it's really interesting. This is specifically regarding closing the loop. So what I've been trying to do recently in the last few days is take some of that extra energy that's not being used and from the pickup coil and see if I can dump it back into the battery to increase the efficiency a little bit. And we know we're getting some usable energy because I've hooked up a light bulb to the output. It's not much, it's a 0.6 watt light bulb, but we're getting a lot of voltage. So we're getting around 30 volts just hooking up the dual thief setup from the output. Without any rectifier or anything, just hooking up the multimeter to the output, the load output of the secondary device, we're getting 30 volts, which is pretty cool. So taking a cue from Mike from Faraday Research, I added a rectifier capacitor rectifier setup to convert the AC into DC and feed it back into the battery. But here's the catch. As it turns out, the system was already producing pulsed DC, not AC, and this is why it was screwing with my readings and my results. Because after hours of tinkering, I found out that adding capacitors between the rectifiers didn't really help at all, but placing a capacitor in parallel with the load before the rectification boosted the voltage from 5 volts to 8.5 volts. So with the rectifier, see, remember, we're getting 30 volts out of the system without rectifying it, the pickup system. We rectify it with Mike's suggestion, and we got about 5 to 6 volts, okay? Not a lot. But removing the capacitor between the two rectifiers increased this to 8.5 volts. So I know it's possible to increase this. It's just not enough still. So you can... see some of the waveforms, because I tried to feed a little bit of this back into the battery, even though it's not really going to do anything. I just wanted to see, you know, make sure it's not going to blow up or start smoking or something. No, it's stable. It just wasn't really doing anything to the efficiency. So, but I did read the waveforms, and I'm going to show you them here. Give me one moment to load it up. So here's the waveform that I picked up when I hooked up the probe to the positive terminal after hooking the Oh, no, wait, I'm sorry. This is the video that I'm catching the waveform outside of the secondary coil. So picking it up outside the load's output of the second lightning thief. Okay, so this, I believe,
All right,
is
so
that
we got
waveform.
the dual thief set up. This is the pickup from the dual thief after it's been rectified through two
Yes.
rectifiers.
Okay, this is...
And it's using the open circuit method of the dual thief pickup device. And look at that. It looks like almost two waveform patterns, like a resonance there. Interesting.
It's hard to tell because this is a really crappy oscilloscope. Very low frame rate for this thing, especially when it's overloaded. You can, like, my system will produce so much voltage spikes that this thing will just crawl to like 1 to 2 frames per second. So I got to be careful with that. But this, it's not as high because it's picking up the wireless energy, but it's still interesting waveform. It looks like a waveform within a waveform, but it's hard to tell.
I don't know if it's just my crappy O-scope or if that's actually a waveform inside of a waveform that we're seeing. So, we'll ask the team about that.
Yeah, so pulsed DC is not AC. So think of turning a system on and off, okay? You're turning it on and off with direct current going one way. But with AC, you're oscillating it back and forth continuously. So it's kind of like a reverb or a rebound effect. So that's the difference. With pulsed DC, you can save energy, but AC seems to work better for some of these coil systems. But I'm starting to think it's not true AC. I'm starting to think it's some kind of synthetic pulsed DC that's just has elements of AC inside of it, which is interesting to think about because that really shouldn't happen, I don't think. But yeah, everybody that I've seen research these Abaha coils and Rodin coils, they all pick up they all read the energy the same way. They read the direct current for the voltage, and then the AC current for the picking up the current with an amp clamp. So, and that's what I've been doing. And you can't pick up the current you can't pick up the voltage when it's set to AC in the system. But you also can't pick up the current when it's set to DC. So it's weird. The current won't give you an accurate reading when you do the math and work out the energy of the system. It doesn't, the math doesn't work out correctly. I think when you're reading the DC current, I think you're only reading a part of the waveform. And if you can read that, you're only getting a fraction of what you're seeing, or you're getting a misleading reading, in my opinion, from what I've experienced. Because the AC current seems to give you the most accurate reading when you work out the math and you work out, the input versus output. So we're going to go back to the screenshot here. We have one more video of the actual radiant energy waveform that I read when it was fed back into the battery. This is what I was originally talking about. So we're going to look at that real quick. This is hooking up the probe to the positive terminal after I've hooked up both the positive and negative output of the dual thief, the second pickup coil circuit, directly to the battery. I didn't rectify it or anything. It doesn't seem like I have to. Again, it's very convenient. So we're gonna take a look at that. Probe off. The probe is hooked up to the battery. Let's take the full bridge rectifier off. Okay, so let's take the cycle and open it up again. open the loop up again. So let's take the rectifier off and stop feeding it the energy and see what happens just normally with the battery. So what I'm doing here is I'm showing you the difference in waveform on the battery's positive terminal compared to when the system is being fed that secondary energy compared to when it's not. So we're looking at the two different waveforms, and you'll notice when it's not being fed that energy, there isn't as big of a like radiant spike on the negative. But once I hook up that that secondary coil to the battery, the positive terminal shows a more negative radiant spike, which is very cool. It's exactly what we want to see. It's not a lot, but it's there, and it's noticeable compared to when it's not. Oh, and it fell off. See? Look at that. As soon as it fell off, you see it shrunk. Look how the waveform changes. It gets smaller. So let's put it back on. And you noticed, so it's on. Notice immediately. See? See that? You see those negative radiant spikes. So I know it's feeding it back into the positive, which is what we want. So it's doing something. It's doing something. Maybe it's putting a little bit energy back in, not enough to fully close the loop, so to speak. But, you know, maybe we need, but maybe enough to increase the efficiency a little more. We'll see. Yeah. So maybe we need to condition the battery, because I know sometimes some fringe scientists and inventors like John Bedini will emphasize conditioning a battery so it can take a negative energy charge. So maybe that's what we have to do and condition our battery. I'll have to talk to the team and see what they recommend. But this is all very cool, very interesting developments. But this isn't even the tip of the iceberg, ladies and gentlemen. All right, so what exactly are we looking for in the waveform? Well, John Bedini will tell you that we are looking for, oh, give me 1 second to scroll down. That right there, what he drew on the board in the top left corner. It's called an H wave. It has an initial large radiant spike, and then it kind of comes down in an H bump fashion. I don't know what you would call it. It just looks like an H. But that is what we are looking for. I don't think we've quite found it. We've found waveforms that look similar, and like Gerald indicated, you know, we kind of had a half H waveform at some point, but it wasn't a full H wave. Either that or my oscilloscope is just too crappy to read it properly. That's always a possibility. Either way, we have some interesting developments outside of that. So this is where things took an unbelievable turn regarding the 0.6 watt LED magic, and something amazing that happened last night. And instead of focusing purely on rectification, I decided to see how the system responded to different load capacitances. Because I kind of came to the conclusion this energy already seems to be like a pulsed DC already. It doesn't need to be rectified. In fact, rectifying it actually just kind of diminishes it and wastes the energy potential, bringing the 30 volts down to, like, I could only get it up to 8.5 volts, and that's, you know, screwing with it all night. So I just decided to, you know, throw aside the rectifier for a moment, because the PCB of the Lightning Thief does have a slot for adding a capacitor in parallel if I wanted to. And I did. You know, I added a 330 picofarad capacitor just to see if I could smooth out the signal. Maybe it would help a little bit. And I bought more 0.6 watt LED bulbs because they were singing to me, indicating, you know, they might be interacting with the system in a very interesting way. And they are. They are. And I wish I could grab more today. I tried to go and grab more from the dollar store today. I grabbed all of them that I could. I only have 3. I wanted to grab more to include with the prototypes, but we'll see if I can go to another dollar store and see if I can find some, because they're truly remarkable. But I'm assuming they would only work with my size coil. I don't know. I haven't tested out the Fireball coil because the Fireball coil is on the fritz. It's been on the fritz for a while, and I haven't had time to fix it. I did untwist all the connections, but yeah, one of the connections wasn't making continuity, so I had to put that aside, unfortunately. It's not that it's not fixable. I think I could fix it. It's just going to take some time, and I'll have to set some time aside to mess with the Fireball coil to tell indefinitely if the 0.6 watt is unique to my coil or it's just going to work with the system in general. Now, I added one more 0.6 watt bulb to the primary, increasing the pickup coil voltage from 30 to 32. This is what was really cool. Cool. I finally got some extra 0.6 watt LED light bulbs. So I have 2 of them hooked up, and I'm going to plug in a third 40 watt panel. And check this out. Watch this. Okay, so this is the dual thief picking up wireless energy. You can see the HV being picked up from the coil, right? We detune it, and it goes off. So it's in tune, picking up 30 volts. Look at that. 30 volts DC, free energy. That's not affecting the light at all. So check this out. I just have the 2 6.6 watt LED light bulbs hooked up, just the 2, and then I'm going to plug in the 40 watt. And look what happens to the voltage on the pickup coil. Watch this. Okay, I'm going to plug this in. It starts singing too. 2 volts to 32 volts. When I plug that in, and then the light bulbs stay on. They stop blinking. So it's like the system kind of stabilized a little bit and increased the output for the dual thief. Real quick here, I'm measuring, I don't know if I'm measuring the wrong positive, negative, I'm getting them mixed up, or this, it's either that or it's actually getting negative 32 volts, which if it is, it would be very interesting. This is something that I have to sort out too, because if I mix those 2 up, sometimes it sends energy back into the PCB board and blows it up, blows the line up, because there's a line directly to the, I believe, positive on the PCB. So, yeah, that's something I have to sort out with Michelle, figure out which one's positive and negative, because it is important to determine if this is positive energy or negative energy coming out of here. I think it's negative voltage. In my opinion, I think I have it hooked up right. Otherwise, the PCB, I think, would have blew up like it did before. But you know, I have to, that's warranting further investigation. We can't say at this time. Pretty cool. Yes, pretty cool indeed. All right, so after that, I hooked up another 0.6 watt bulb to the output of the secondary Lightning Thief device. And what happened, I couldn't describe with words. It was so phenomenal. I just have to, show you. I can't spoil it. I have to show you the video. I don't want to spoil it with the words that I have written. It doesn't do it justice. I have to show you guys. Check this out. So I have right now the dual thief set up.
I have two of these 0.6 watt LEDs. This one's hooked up, and this one's going to be hooked up in a second.
Hey, Mitchell, glad to have you here. It's okay. This is a safe space for laymen's as well as enthusiasts who are already familiar with this stuff. So I try to break it down for people in a general way. So hopefully I do that well. If I don't, if you have any questions, just leave them in chat.
So I have right now the dual thief setup. I have two of these 0.6 watt LEDs. This one's hooked up, and this one's going to be hooked up in a second, but this is the only one hooked up right now. So we have one hooked up to the primary and the 40 watt, and the second one is just hooked up to the secondary right here, not hooked up to the power. So we're normally getting 31 with just one. Now we're going to screw this in to the secondary, and watch this. As we screw this in, it jumps up to 43.
Wow.
Doesn't light up, but the voltage jumps up to 43.
Because again, the light bulb is acting as a capacitor itself. It's tuning the system by adding these light bulbs.
Screw it back in.
And what's cool is you can tune the pickup coil system by adding capacitance to the primary. So it's all in resonance and it all affects one another. It's really, really cool.
Back out.
So I'm taking it
Back
out
in.
and putting it back in.
Now, I'm curious because I don't
Hey,
have this
Joe.
one hooked up. Let's
Good
plug
to have
this
you
one
here,
into
buddy.
the primary as well. So we have two in the primary.
Look at this.
Let's
This
see
is
what
so
it
cool.
does.
It's not affecting the current at all.
And it doesn't affect it at all. Let's take a look at the current. Still 38.
Yeah.
No matter what we do. Oh. Yeah, 38, 39. It's around the same range that we were before, so we haven't really affected it that much. We could detune it and it goes off.
So, and again, we are only looking to get 12 or 13 volts of that back into the battery and maybe reduce that voltage a little bit and add some current, if that's possible. Convert some of that voltage into current. And we only need like 12, 13 volts, and we can essentially, you know, kind of charge the battery a little bit while we're using the system with the secondary pickup, which I think is phenomenal. I think it's an extremely important breakthrough, and if we can crack this right here, this is what we need to actually close the loop in our system, and that was the whole goal of phase 2, is closing the loop if we could. And I thought it could take years, and it could very well take years, but I'm hoping that this is the route that will take us there using this pickup method, because it's not affecting the system at all. As you'll see in a minute, actually, it might be reducing the current with a certain configuration, which is extremely WTF.
Oh, wow, it goes up. Oh, wow, it's going up. We haven't really affected
you see
it
that?
much.
You see
Goes
that?
off. Oh, wow, it goes up. Oh, wow, it's going up. 62.
I detuned it, and obviously, I mean, I didn't even think about doing it, but it went up because it's not going to the neon bulb anymore. But I thought the frequency would be affecting it. I detuned it, and it went up more. That's not the last of what I discovered either. This is insane.
Holy crap. What the F? I detuned it and it shot up. Now keep in mind, before this, 43, and then
Wow.
unscrewing this at 31, before this, I was only getting 4 volts without the resonance relay here, the diode. So this is a diode forcing it into the positive. So we plug in.
That's right. Also, without the rectifier, we weren't really getting that much voltage until I hooked up that diode. So that diode kind of helped capture some of that energy and direct it to the load, which is where the multimeter is hooked up to.
We go up to 42, 42, 43. Okay.
This is so insane.
And then we detune it and watch it go up. Wow.
I mean, it makes sense though. I have all that voltage to excite the neon lamp. We just needed to figure out how to get it into
Turning
something
it back
usable.
down. Makes sense because the neon's the neon's going out.
It's not affecting
42.
the primary at all.
That goes off, and this is going up. Wow, so cool. There's got to be a way that we can use this. 61 volts.
So, Elijah Tax said, Ben, when you detune it, you created a subharmonic carrier frequency, like sawtooth wave decomposes into both low and high frequency, oscillating back and forth. I'm going to have to do some research to fully comprehend what that exactly means, because you're just on another level than I am, Elijah. But you might be right on that. It's doing something that I just don't understand at this moment, and it's doing something phenomenal. And look, the current went down. The current went down.
From the batteries. Yeah, it's
went
going down a little
down.
bit. That's weird.
What the? You guys, this is incredible. I got my whole mini lab powered by radiant energy now, or lighted by radiant energy. Oh, I love it. It's so cool. This is such a huge breakthrough right here. I'm so happy with these results. And we have another interesting part 3 to this. So be prepared for another one.
Just another video, part 2. It's at 60 volts. This is screwed in. We're going to unscrew this now and watch what the voltage jumps down to. We're unscrewing it.
Oh, that might be the wrong video.
But
Yep, that's the wrong video. So we have one more video I wanted to show you. Give me one moment. I think I have... Oh, there it is. Okay. There it is. So this is when I removed the 330 picofarad capacitor. Okay. I forgot I had it attached, honestly. I shouldn't have attached it at all, because check this out.
one more for you. So we have 37 milliamps coming out of the battery, and then 59 volts coming out of the secondary pickup. So check this out. We unhooked the 330 picofarad capacitor from the open circuit pickup. Unhook it. Just unhook it and look it spikes up to 68. So we didn't need it. We might not need it. It might be the wrong one. And not only that, the current drops down a single milliamp to 36.
Oh my god!
So I thought that was very fascinating.
Dude, I don't have words for this. I just don't. Yeah, I don't need to put on the lights really anymore. I mean, there are a few instances where it isn't bright enough to light in certain scenarios when I have to look for something maybe. But in most cases, I don't really need to turn on the lights in the living room at all. They just hook up to the battery and they just last all day, and you know, this system will last, you know, 2-3 days like this. I actually haven't really pushed it yet. I should probably do another time test to figure out exactly how long it'll last now with the recent configuration tweaks. Because again, we added the resonance relay. We added the secondary 0.6 watt light bulb and the pickup, the dual thief setup, and figured out it was detuning, increasing the voltage while we detune it. So that actually reduced the current to 36 milliamps. I think we should do another time test to see exactly how long that system will last like that. And if we can draw extra free energy out of the system with that secondary pickup while reducing the current draw on the regular system, not putting any strain on it, actually relieving some strain, it seems like that's incredible. Because that's what it seems like it's doing. It seems like it's not putting a strain on it. It's relieving some of the extra energy maybe that the coil can't get rid of. I don't know. I have no idea. Yes, thank you, Elijah. I appreciate that. This is a very, very big moment for my research. So it's mind-blowing, right? But here's where things get even more interesting. When the LED bulb on the second lightning thief lights up, it actually shows 5 to 7 milliamps of current without affecting the regular system at all, mind you. So it's tiny, but it's usable. If we can effectively feed that back into the battery, we could be looking at an incredible energy recycling loop. So even if it's 7 to 10 milliamps with that voltage, 12, 13 volts, that's just a little bit, not maybe enough to close the loop indefinitely, so have it run, for, indefinitely until the parts wear out, but it might be enough to extend the life of the system and increase the efficiency. Because again, we're wasting energy if we're not recycling it back into the system. So where do we go from here, though? And what does all this mean? Well, we're still in the early stages of understanding exactly why these 0.6 watt bulbs interact with the system the way they do, but what's clear is that the resonance, capacitance, and load characteristics all play a crucial role in maximizing efficiency. The next step is to further refine the resonance relay by trying different types of diodes. I've already ordered a high-speed one, a nice high-speed one. I forget what model. But ideally, we would want to test with a germanium diode. Now, it's going to be a little harder to find. We also need to fine-tune the dual thief in order to close the loop, to recycle energy more efficiently in our system. So if this experiment has proven anything, it's that small adjustments in load configuration can lead to massive increases in voltage and efficiency. With that, we're going to do a quick segment on what Michelle is currently working on. So we're going to take an update on what Michelle's working on, and don't forget to subscribe to Michelle's Bench, Michelle's YouTube channel, where if you want some of the breakthroughs that we've been coming across and some of the recent developments in our research, definitely subscribe to my channel and Michelle's, and I'll put his channel in the chat momentarily. Give me one moment. And we're going to put that here. All right. Learned that from Dr. Rife. Wow, did you know Royal Raymond Rife?
Auto-generator of Richard Viley, Part 1 half PAR, Hask user, version due February 10, 2000.
You can spread those pulses with a transformer to so many different places without putting any load on the system that makes the pulses. Yeah, I was thinking about using a transformer. See, I have here, I'll show you guys. This is the paradox box. So this is the paradox box. It's basically two strong magnets glued with each north pole facing each other. I don't know what Michel used to glue these together, but he did a hell of a job. This is a solid. It acts as a transformer and an inductor, really. But it's two magnets glued together, north poles facing each other, and a bifilar coil wrapped around it. So he says that he's able to step up voltage and maintain the current, I believe, or step up current while maintaining voltage, one or the other. I did notice some interesting minor effects with my system when I hooked it up, but we're going to need to do further testing. But I think we might be able to use something like this for what you're talking about regarding using a transformer to maybe amplify some of those signals and send them, like you said, to other places. Maybe another battery. Maybe that's the solution. You know, Bedini's original schematics for the schoolgirl circuit included, you know, one primary drive battery and a charge battery. So, you know, maybe we just need another battery to dump that energy into instead. Condition that battery. That might be the route to do it. Oh, thank you, Alex. Thank you so much. He says, kudos for taking the Thief series of circuits so much farther. We are trying to push the limits of what is known to be possible with these circuits, because at the end of the day, they're grossly misunderstood. Most people just think of them as amplification, you know, self-oscillating circuits that amplify energy or amplify voltage. But they're not just amplifiers. They're meant to amplify energy, self-oscillate your system, and capture back EMF. So if you're not capturing that back EMF, you're not utilizing the Joule Thief correctly, because that's what it's meant to do. It's a remarkable circuit that's kind of, I think, intentionally, maybe intentionally, been misconstrued as just a simple resonance circuit. Alex says, if I understand correctly, you can use pulses for so much. They travel well, and they can charge batteries or caps or do hydrolysis or run lights. They're so yes, exactly. They're versatile. You can exactly do it for electrolysis, what Stan Meyer did for his water-powered engine. You can put them into capacitors to, power things or charge batteries with them. You can also use them to condition batteries. Pulsed charges break up the sulfation in batteries, lead-acid batteries. So that's always a plus. Like you're literally you're performing maintenance on your battery while you're using it. It's a pretty useful type of setup. So yeah, let's watch what Michel's been working on. He's been working hard translating some of Richard Vial's work. And Vial was working on something called an auto generator. And in our previous podcast live stream, we showed Michel's cold current demonstration from this auto generator. He actually built one. But he's been going through and trying to translate some of this stuff from French, which has been extremely tedious. But I wanted to take a look at some of it. So let's load up some of it and just take a quick peek.
At 17.01 disclaimer, Richard Vialese has released the below information to the public domain for over 45 years, therefore no patents can be filed.
Oh yes, that reminds me. We also do have a piezoelectric transducer that we can use for the system as well to try and maybe help recycle some of that energy that's being wasted.
First auto generator test, solid copper bar setup. Richard Vialese's first auto generator was made up of two identical half bars of solid copper 24 cm long and of rectangular section 1 cm x 3 cm, separated by electrical tape. thickness 0.5 millimeters, stuck on one of the ends of one of the half bars so that once in contact with each other, there is no electrical conductivity. These half bars were taken of this size because they are a recycled element, and Richard Biley made do with what he found. He was looking for a solid material, and that was the only thing easily available. The whole thing was wound by two parallel telephone wires of 0.5 millimeters copper diameter each, with approximately 0.5 millimeters of sheathing diameter, one red and one white. In fact, for practical purposes, the telephone wires were wound on a plastic support of rectangular section serving as a sheath for the half bars, which were slipped into this sheath. Richard Biley could slide the half bars into the sheath more or less and remove a large part of a half bar at will. The purpose of parallel winding is to help reduce the skin effect a little. The resistance of the wires increases with frequency. This effect decreases with the diameter of the wires. Smaller wires, less resistance due to skin effect. The ideal would be to have thousands of wires of micrometric diameter and isolated from each other to reduce the skin effect.
So this device is extremely simple. Extremely simple to build. We can actually watch briefly the short video that Michelle did that shows you a little bit of its construction. But it's very simple. It's basically two tubes with a insulation between them, and then you have one wire wrapped around it. He wrapped it counterclockwise, and then you put two terminal heads at either end. I mean, it's extremely stupidly simple. Anybody with some, garage tinkering skills can whip something like this up in a matter of, 30 minutes or an hour. Granted, they have the proper materials and tools at their disposal. Someone like me, it might take a little longer because I have to jerry-rig stuff. I don't have proper tools. But yeah, this is very cool stuff. Let's watch a little bit of this. Then we'll take a quick break and maybe head over to the lab to do some demonstrations of the system if you guys want to see it in action, or have any questions. We can do like an interactive portion of the Benefactor's Guide to Free Energy Devices. Tonight, we're actually focusing on my own research. The previous episodes of this series, we actually were diving into the Practical Guide to Free Energy Devices book, the 2017 rare edition that I have. We go over some of those devices and some of the easier ones and more viable ones for replication purposes, and maybe explaining some of the science and making connections to my own research as well. But yeah, tonight we're going into my own research. But I wanted to do a quick segment to give a shout out to Michel, because he has been working with me in the background, doing remarkable research, and he has been working hard trying to translate some of this for you guys. And I haven't had time to watch it, so honestly, I'm watching this for the first time too. I'm curious to see what Vial has to say about the autogen, and we're not gonna watch the whole thing. If you want to see the whole thing, I have Michel's bench, Michel's YouTube channel linked in the chat. I will put it in there again in a few minutes, but I just wanted to take a look at some of what Vial had to say about the device himself.
Lit's wires, but the input loss is already so low that trying to reduce it further with a purchase so expensive as Lit's thread at this level is a real unnecessary waste. On the other hand, it will be very useful elsewhere, in the exit agreement, but we will talk about it in the U-shaped self-generating device where it was created by Richard Biley, to keep the historical aspect of the work. Here there are two isolated ones, the red wire and the white wire. This is not much of an improvement over a single wire, and it might not have been done. A hole is drilled at the end of each half bar with a screw and a bolt placed in it, allowing an attachment area to be made on which an alligator clip can be attached. At the input, a function generator is connected directly to the two ends of the winding wire which surrounds the sheath, without an amplifier in this first low-power version of the auto generator. The generator that Richard Biley initially had was an old needle generator which did not go below a limiting frequency. It seems that 10 MHz was the low limiting frequency. It delivered 4 to 8 V effective at the output depending on the frequency, voltage decreasing at the output with increasing frequency. At the output, we connect a conductive wire to the ends of each half bar of copper, using an alligator clip, and we connect them together, creating a short circuit between the two half bars. This is achieved by a laboratory cord with 1 mm diameter copper wire with banana plugs at the ends called 1 meter long, but measured at 121 centimeters from the tip of one banana plug to the other tip, each end banana plug measuring a total length of 4.7 centimeters, connected to crocodile clips. This short circuit is essential for the proper functioning of the auto generator. In fact, the leakage choke of this wire has an impedance at the operating frequency which produces a voltage across the wire crossed by the current leaving the half bars. So this short circuit does not cause the voltage to drop to zero, as one might falsely think. This would be true in direct current. Without this wire, the voltage across the wire, and therefore the half bars, is high when empty, but it collapses as soon as you plug in a bulb, even one of low voltage, which only lights up very dimly. With this wire, we obtain sufficient active power to light bulbs of various sizes, 2.5V to 6V, quite brightly. There is no significant voltage collapse effect. The measured no-load voltage was around 11V with the wire alone. Furthermore, when Richard Viley removes the electrical tape which separates the two half bars and places them in electrical contact, there is no longer any voltage at the terminals. The self-generating effect has disappeared. So electrical insulation, Scotch tape, air, plastic, is essential. We therefore also connect to the terminals of the wire, therefore to the terminals of the half bars, a load, electric bulb, by wires terminated by crocodile clips. Setup of the experiment, we set the input of the function generator with a sine wave signal with a frequency of 25 MHz. It is at this frequency, in fact between 25 MHz and 27 MHz, the display not being precise, it only had the reading to the nearest megahertz, that the auto generator worked best. The bulb, 4V/40 mA, connected as a load lights up with good brightness, consuming approximately its nominal power of 4V/40 mA equals 0.16 watts. When the two copper half bars are joined together, the total length immersed in the magnetic field is 48 cm equals 0.48 m. According to the resonance calculation formulas of Richard Viley, see below document, we should have an adapted resonance frequency of f equals 5.18 MHz. However, the function generator he had did not allow him to work at this frequency. Note that the frequency on which the auto generator operated is approximately 5 times the tuning frequency, the fifth harmonic. It is on this harmonic rather than on another that he obtained a maximum power output, visible by maximum illumination on a bulb. Since then he has a digital generator capable of all frequencies and has obtained 100 times the output power of the first auto generator in the current versions. The bulbs mainly used were 4V/40 mA bulbs. Why was it on this harmonic 5 rather than a lower or higher harmonic accessible to the function generator that we had the maximum power? Richard Viley does not have the answer. He did not study the behavior outside the resonant frequency in harmonics. He couldn't work on the main tuning frequency at that time anyway, having no other function generator at his disposal, and observed what he could obtain. Modification of the material of the half bars. We can replace one or both copper half bars with a plastic half bar of the same size, or simply let the air serve as a half bar. What must be understood in Richard's theory, and which we also observe in experimental practice, is that copper, or plastic, or air do exactly the same work of creating electrical energy by electrons bound to atoms of copper or plastic or air. Whether the material is a conductor or an insulator, the magnetic field surrounding them makes the bound electrons of these atoms vibrate, and therefore Richard Viley's principle must work with insulators too. On the other hand, the number of linked electrons being different, the calculations then differ for the current and voltage generated. And the big difference is that since air or plastic has no free electrons, there will be no hot current, circulation of free electrons in the body of the half bars. This changes the power produced at the output. I was able to observe at Richard Viley's, the first time I saw him, in the company of Elaine B., that by inserting a half bar of plastic in place of each half bar of copper and placing the crocodile clips on it, the bulb at the terminals lit up. Still with the short circuit wire. It lit up more weakly, but lit up. Same thing by removing the half bars of plastic and leaving the inside empty, i.e. filled with air. The bulb lit up even more weakly than with the plastic. There the crocodile clips had to be held with the hand in the air, in the center of the two exits of the sheath. Surprising, isn't it? In the case where we decide to take the output voltage at the terminals of a piece of plastic or a column of air that replaces the internal copper, it is still necessary for a piece of the crocodile clip of the conductive wire that is connected to this piece of half bar of plastic, or in the internal air, to be immersed in the magnetic field of the winding that surrounds the sheath, to also be part of the device and for the free electrons of this piece of wire to be set in motion in order to be able to create a current that will flow through the external circuit. If we place the crocodile clips at a distance from the ends of the sheath, nothing happens, no lighting. They must enter a little into the internal magnetic field. Research into the possibly normal origin of this energy output. After seeing this at Richard Biley's, this aspect of output production without a half bar of copper inside made me think that the output current could be just a normal effect due to a capacitive coupling between the winding serving as a capacitor plate and the crocodile clip, or any other piece of the conductive wire, serving as a second plate, the air and the plastic of the sheath separating them being the dielectric. Finally, the crocodile clip would only derive current from the input, a current that would not come from any abnormal effect. After discussing it at length with Richard Biley and tests and measurements were carried out by me as well as by Elaine B. and Richard Biley, we can affirm that it is absolutely not a capacitive coupling that derives energy from the input that can explain this phenomenon. The arguments that show that this is not the case, the calculation of the current flowing in the very bad capacitor constituted by the coil/crocodile clip capacitance shows that we should really have much less than what comes out in the bulb. Considerations on the potential differences necessary to set the currents in motion by this capacitive effect by having done numerous tests of connection of certain points to the ground show that there is not a sufficient potential difference. And short-circuiting tests of this pseudo-capacitive effect by aluminum sheets connected to the ground of the function generator show that the output production remains present, very slightly reduced. So a capacitive effect, there may be one, but it is largely negligible compared to what we measure, and also the current calculations, measurement of potential difference and short-circuiting experiment of this effect show that a large abnormal effect remains which is not at all explainable by the capacitive derivation from the input. Electromagnetic radiation cannot explain what is obtained either. Not only does the calculation show that the coil made by the wire surrounding the sheath has a length totally unsuitable for radiation of the emitted wavelength, even by harmonics, but in addition the radiated energy is not sufficient to cause lighting by induction effect. Finally, wrapping the entire half bar with its winding in a sheet of aluminum foil grounded showed that the output production was still present, but reduced. In fact, the frequency of obtaining over unity was modified. By modifying the frequency one could obtain the same brightness. So radiation is not the cause either. In any case, to conclude, the measurements of power actually consumed at the input were then able to show that the input power is much lower than the output power, whether the input power is then radiated or capacitively coupled to the output or by any other artifact, and the Joule effect losses in the input winding that consume it. This shows that there is an anomaly and therefore indeed over unity. Input and output power measurements. 1. École Polytechnique de Lausanne, with an oscilloscope in the physical measurement laboratory. When Swiss sponsors contacted Richard Biley, he had this self-generating device. He was invited to come to Switzerland with his self-generating bar and his function generator.
Just want to interrupt real quick and let everybody know that we do have awesome merch available in the description of the video on our Streamlabs merch store. This is the Benefactor beverage containment unit. It keeps it hot, it keeps it cold, but ice is not included.
To power it. They organized a measurement of the input power and the output power by a person working at the École Polytechnique de Lausanne in Switzerland, in the physical measurements section. There, a physicist, a specialist in sound and waves, used a high-performance oscilloscope and a 1 ohm metal resistor to measure the voltage across the input winding of the auto generator and across the resistor that had been put in series. With the resistor in series he determined the current, and he measured the cosine of the phase shift angle. An internal calculation function of the oscilloscope gave the power with this data. During this time the auto generator delivered 0.16 watts on a 4V and 40 mA bulb. The measurement carried out gave an input consumption of 0.000001 watt equals 10 to 6 watt, or, COP equals 160,000.
Oh, look at that. See, look at that. A COP, a coefficient of performance of 160,000. WTF, ladies and gentlemen. WTF. Let's go back and look at the device that Michel has constructed, the AutoGen, his replication. It is cold current technology.
Current.
So that's a demonstration of it.
A technology that is long overdue, and that hopefully we'll all be able to use very soon. And again, this information has been released in the public domain over 45 years ago. So no patents can be filed. This device you see in front of you is called an auto-generator. This device was invented, created by Richard Vial. He was a physics professor born in the 1940s, and he was a physics professor for 40 years, so pretty much most of his career. Very prominent researcher, and he has made some incredible discoveries related to cold energy. And when he released that information back in the maybe early 80s or even before that, a lot of people were not really open-minded enough to understand that there is a cold side of energy. And so he carried on doing his research, and he was eventually approached by some Swiss investors who wanted to get him to sign a non-disclosure agreement and essentially take away all his discoveries and invention away without the public knowing of.
And that's what we hinted on in the introduction video, black shelving. So a company will come along and offer you a lot of money for your device and put it on a shelf and for nobody to see ever again, because it interrupts the market. It interrupts the macroeconomic status quo, as it were. So, and the system that I'm developing isn't going to be disruptive, but it is going to be a good backup system in case our current grid fails us, which, if you live in America, the American Society of Civil Engineers rates our infrastructure D+ on a regular annual basis. So, yeah, we have frequent blackouts, frequent times where we have, even brownouts, stuff like that, where your devices will even, fry out. So you want some kind of, or at least I wanted some kind of off-the-grid lighting, heating system, and eventually we'll be able to develop this to charge devices too, hopefully. But for now, it's just an extremely extremely efficient lighting system. So, yeah, black shelving is a big problem in our industry, especially for inventors and fringe scientists who just want to do the work and get the information out there and want to see their inventions benefit, humanity. Companies like to come along, offer you a lot of money, and just, shelve it. And they'll butter you up too. They'll promise you the world. Oh, we'll put this out to everybody, every household, and blah blah blah, yada yada yada. I think something like that happened to Daniel and Erica Nunez, to be honest. I think they partnered with somebody who was shady, took a contract deal that they didn't read through thoroughly or understand or comprehend enough. And when they signed it, the company, and this happens sometimes, the company just takes their IP. You're like, oh, yeah, we own this now. Take all your videos off of YouTube. We don't want you to put any of this information out in the public anymore because it belongs to us. You signed the contract. You should have read the fine print, basically. I think that's what happened to First Stop Energies. We haven't heard from Daniel or Erica Nunez in over 2 years now. Their website suspiciously has been updated right when the domain expired, and it said new products coming soon, but that's been for like 6 months already. It said that. I'm very skeptical. It looks very suspicious. If you read the website, it actually says, if you leave your contact information, a real member of our team will reach out to you. That kind of wording and terminology, it just screams like suspicious to me. I think the company screwed them, and they don't want anybody to know that they shelved this technology. But it doesn't matter. Everything that I'm developing is non-patented. You can't patent what I'm developing. You can't patent the Lightning Thief. Michelle and I discussed this thoroughly. We don't want anybody coming in and putting a patent on this stuff. We want everybody to be able to utilize it. And even if you want to sell your own version of the Lightning Thief, I don't care. I just want the information out there. I want the devices to be utilized in households. The technology is real. People aren't utilizing back EMF. They're utilizing inefficient inverters for the same, setups. So imagine going camping, taking a 20 amp hour 12 volt battery, which cost me what, $25 on Amazon. Imagine taking that camping, getting your Lightning Thief and your little Mark I coil, which will be included in we'll have a little carrying case that you can buy for it. And imagine just, going and hooking up all your lighting for your camping to that and having the entire week it just powered off of that 12 volt battery. That is pretty extraordinary, if you ask me. Again, a normal inverter at 100%, granted it was 100% brightness, it only got about 10 minutes on my 12 volt battery when I hooked up a standard inverter. So this is, compared to my lighting, which, is only maybe about 1 to 2% bright, but it's bright enough. It's a 40 watt panel. That's designed for like a big industrial situation. So, that's lasting 48 hours. So it's insane. Or more than 48 hours.
Life-changing discoveries, and he decided to release gracefully this information to the public domain over probably 45 years ago now, and this information has almost been lost.
So Alex says, I'd like to help you sell kits for these, and I respect that you offer all your devices for free. Yes. Email me. I'll put in my email. It's beneficencetv@gmail.com, but I'll put it in the chat in a moment. Yeah, you can email me if you'd like to help try to get these devices out. I am starting a Coil Kits lab shop where you should be able to make your own kit. You go on there and you pick what coil you want, what device you want, Lightning Thief, Pulse Motor, which is the green machine, all sorts of stuff. And you can build your own kit. Basically for either experimentation or lighting, off-the-grid lighting purposes. We're working on heating at the moment. We haven't cracked it yet, but it shouldn't be too far off until we develop something for heating as well. But yeah, reach out to me at beneficencetv@gmail.com, and we can definitely use some help getting these kits out there. And again, all the information is in the public domain. We have tutorials on how to build all of this stuff. I've released, and Michelle has released, all the information on our channels. If you want to go ahead and build a Lightning Thief right now, if you have the skills and you have a 3D printer available, you can go ahead and do that. And I encourage you to do that. I want this device to be beta tested more before we come to a consumer version, because I want to work out all the kinks and the flaws. And when we go into our lab here in a few minutes, because I decided to do an interactive lab tonight. I wasn't sure if I was going to do one, but we got a lot of people interested in the Lightning Thief now, and I want to be able to have the opportunity to have an interactive lab where I can show off the device, what it's capable of doing, the questions that we have for it, maybe that some people can help us with, and also, you know, what our new breakthrough discoveries have been in the recent weeks, specifically the resonance relay extension wire, which is just a simple high-speed UF4007 diode attached to an extension wire. It's attached, but the placement of it is everything. So it's very, very significant to utilize the back EMF properly. And that's what we've been trying to do, is tune the system and try to capture and recycle as much of that back EMF that we're generating. And we are seeing a lot of free energy being available with the pickup method, which is very exciting.
On the internet, and I have luckily managed to retrieve this very precious information. One of the issues has been that a lot of information was actually in French. And so I have painfully taken the time to translate the first document, which is part 1, which I've translated for you all to read and understand this technology, which is the technology of tomorrow. And so this device here...
Winding a 4-foot coil by hand, what a nightmare. Well, we've been trying to develop easier ways to wind coils. And I don't think there's any like easy method to do it with the ABHA coil. You have to really do it by hand with that one. But with, you know, cylindrical coils like this, you can maybe use like something like a power drill, you know, and kind of put it on a low setting and just wind it that way. I've seen that setup, and it seems to work really well with Tesla coils and people who don't want to sit there and wind a very fine wire very methodically, and you know, they just want to, you know, set something and kind of just roll with the flow of the motor. So that's always an option if you are finding it tedious to wind something like this. But this, you know, this is a pretty simple device regarding what it's capable of doing.
Here
again, he's not really feeding any energy in here, just a frequency. He's just putting a frequency in here, and he's lighting the freaking light bulb. I mean, come on. Bill Nye has to come on here and explain what's going on. He can't. Not in a million years, not with conventional science, because Bill Nye is not going to know what the hell cold current is. And this is something that's a big problem with society today. Is we have especially all these celebrity scientists like Neil deGrasse Tyson, and they're so closed-minded that we're never going to figure out what's going on with the universe if we listen to them. Like it's just never going to happen in a million years. You're never going to figure out the secrets of the universe by listening to somebody like Bill Nye. As much as I love the guy for being a staple in my childhood in conventional science, he's great. But being open-minded to the new science and potential of, you know, plasma physics and plasmoid technology and free energy technology from the vacuum, never going to happen. They're just too stubborn, and they have too big of reputations to maintain, to admit that they were wrong all those years. So we might actually transition into a quick intermission while I get set up for the mini lab here. But first, I just want to show you, do I have it on here? Nope, I don't have it. So yeah, we're going to transition to an intermission while I get set up for the interactive mini lab, where I go over the Lightning Thief device and some of its basic functions, how you set it up, all that good stuff. So stay tuned for more right here on the Benefactor's Guide to Free Energy Devices. Radiant energy lighting. Move out my way, box. All right. I'm gonna plug in the system at the bottom with the 12-volt battery. Gotta turn the lumen lamp on the left there for some ambiance. Alright, so everything's plugged in. As you can see, we have two 0.6 watt LEDs hooked up. One on the left and one on the right here, and a 40 watt panel at the top. And that is hooked up directly to this primary, which is hooked up to this Mark I coil at the top, and that is hooked up to the battery at the bottom. I'll show you in a minute. So this is the 330 picofarad capacitor we had hooked up to the secondary here at the bottom. This one has two outputs for the capacitor that's in parallel with the load output. It's purple and green wire right here. And I had that hooked up, and once I unplugged it, we got this, which was about 67, 68 volts coming out of that secondary. That's not hooked up to the battery. So that's our battery back there. This is our railing for the light. And this is not at all hooked up to this right here. This is just hooked up to the multimeter and this right here. And it's hooked up to the coil that's sitting below the Mark I. See the Christmas coil below it? And that one's actually missing an entire wind. So it's still quite efficient. Without that wind, you can see we're getting about 41 milliamps draw on the battery. Not bad at all. And let us unscrew this, which is adding capacitance to the pickup, and you'll note the drop in voltage. So adding this, even though it's not lighting up, it's tuning the system, the pickup system, to, oh, look at that, it's even increasing the voltage more. So over time, it seems to increase its capacitance slightly. And this is a normal feature of these coils. Until it hits its threshold, which might be the 70 mark here. Let's unplug this. Let's unscrew this. And notice immediately it drops. Good. See that? And that's because we have it fully detuned. We can tune this up, and this is what we were measuring earlier in the video that you saw. This is actually what happens when you unscrew it when it's detuned. 0.060 volts. Plug it back in. So the jumper for the light bulb got unplugged here. Just plug it back in real quick.
There's a light within the dark ways, guided by echoes and ancient ways. You will find one reflection. Within me there's a connection. Feel the pulse, divine sensation.
You know what I should do is just solder these on here real quick. If I can't get it in a moment, I might just do that, ladies and gentlemen. I might just solder it on here because it's having a trouble sticking in this little terminal. Work. Come on, baby. That one in. And we got this one, which is the positive rail with the diode. This is the resonance relay right here on this line. All right, I think that's all hooked up now. I'm gonna plug it in. All right, and as you'll see immediately, we start charging up. we're getting about 40 milliamp draw on the battery right now. Charging up, we're at 52 volts, 53. I'm going to take a look at the wave signal here, the waveform. Let's lower this a little bit, like that. We're up to 58 volts and going strong, still climbing. We should see that climb all the way up to 70. That bad boy right up to here on the positive. We want to do after the diode. Let's do after the diode. Got a little line right here. Oh, wow. Look at that. That is insane. Hold on, let me adjust this. That's insane. So what I'm going to do is I'm going to adjust this, so let's go pause it and then bring it up to the screen so I can show you guys. Because this setup is a little bad for this show and tell. All right. Interesting. Oh, so that's hooked up. Ooh, you know what? Let me change the probe position here real quick. Because I just realized this multimeter positive is actually hooked up before the diode. So let's take a look. Right where it's connected. All right, so what we have here and that's 50 volt resolution. So you see those large spikes. Interesting. Yep, and we're up to 66 volts right now. I'm going to try changing the position of the multimeter to move the red probe to be after the diode, because right now they're both hooked up before the diode. I'm wondering if maybe the diode isn't necessary in this case. We're going to try removing the resonance relay and seeing what happens. We're at 41 milliamps on the current draw for the battery. So it went up 1 milliamp. That's interesting. 67 volts right now is registering on the multimeter. We're going to disconnect that real quick. This on. Let's see how we're going to do this. right, so we removed the resonance relay, the diode, and now we've made room with our extension, with our yellow alligator extension clips, make room for clipping on our multimeter right after the diode. So the diode is still on. We just removed it and moved it back a little bit to make room for the multimeter. And then we're going to try it without the diode. So we'll do it two ways. Let's see what happens with the multimeter right now. We're going to connect it. Oh, we're not getting any voltage. Interesting. So let's remove the resonance relay and take another measurement. It's down here. Remove that. That's the resonance relay right there. Just a simple diode, a UF4007 high-speed diode, and I drew on an arrow before I hit it with this heat shrink gun to indicate where the energy should be flowing, because when you cover it up you can't see the diode obviously, and when you put it on there after, it's hard to get it on there because it's so small. But when you have it bigger like that, you can draw it on and then shrink it. Looks pretty cool, works pretty well. So if you're good at drawing arrows or symbols, like a diode symbol, you can easily do that before you heat shrink your, insulate your wire here, and then it'll be like, should be like a perfect or nearly perfect shrink, smaller version of what you drew. Just something interesting. All right. So we're gonna hook this up without the resonance relay. And everything's crashing down. All right, so I'm gonna move this to the floor temporarily. All right, so we're moving this to the floor so I can get a reading without it falling over. Okay, this goes here. This one goes here. All right. Plug it in and see what our reading is. Oh, haha, missing one probe. Interesting. We're not getting any voltage. Circuit's still working. No, circuit's not working. What's going on here? Interesting. Give me a second to double check my wires. Yeah, the lights really twinkle. It's something to do with the 0.6 watt efficiency of the bulb. And I suspect because the lights blink on and off, it's trying to simulate a candle, really. I think that's what the light bulb does, is try to simulate the natural flicker of a candle. which it does really well. It's beautiful. But I think the on and off function of the light bulb itself, the LEDs, plays into why this is so efficient. You know, most lights don't blink on and off slowly like that. It has to mean something. It has to be some kind of, has to be doing something. So, okay, so we're not getting. We're only getting 6 milliamp draw on the battery right now. So something went wrong. Oh, that went really low. What happened? What the heck? Okay, so what I'm going to do right now is I'm going to hook back everything the way it was and see if it goes back to normal, because this is like, it's only showing 5 to 6 milliamp draw on the battery right now. That left 0.6 bulb went out, and now our 40 watt panel went out. So hold on. Oh, I disconnected and reconnected it. That might have solved it. That might have solved it. Yes, it did. Okay, so now we're getting 58, 59 milliamps on the draw for the battery. We're still not getting the voltage, only 0.32 volts. So give me a second. I'm going to hook everything back up the way it was and see if the voltage increases. That's really weird. Okay. Let me just take a reading right here real quick. Yeah. All right, so we're going to disconnect it, hook everything back up the way it was. Oh, my headset just kicked off, so give me a second. I'm going to plug it into the charger. All right, so we're turning off the lights temporarily to hook up the resonance relay. The simple diode. Okay, we got that here. Oh, you know what? I need to put this here first. So I'm going to put this here. This goes here. All right, one more wire. Here. Okay, we're going to plug in the battery. Oh, everything turns on. Oh, my second probe here. Yeah, 32, we're getting volts now. But that's before the diode, with the probe before the diode. After the diode, we don't really get that much voltage, which is interesting. I don't understand it. We're going to try switching the diode on the opposite end
we'll flip around the diode a little bit. Do a couple of different tests with the diode in different positions. Maybe test it on the opposite rail. See what happens. Let's see. All right, we have the diode facing the same way towards the load on the opposite rail now. We'll turn on the power and clip the power in and see what happens. We're getting an increase in voltage, but it's only 21, 22 volts. Let's put one on both ends of the rail. I have another one here. I made a whole bunch of them. Let's put one on the other end on both ends and see what we get. All right, so we're gonna put one on the opposite end as well. Put one on both ends. See what happens. Plug it in. Sometimes you gotta clip it and declip it. That is so weird. Now we're not picking up any voltage? Hold on. Maybe there's a loose wire, that's why. 1 second. This came undone. Getting that much. That's weird. 42, 43 milliamp draw. Only 0.010 volts with both of them hooked up. Maybe we got a loose connection here. Let's see. No. All right, so we're going to take one off. Actually, leave that one on.
back in. Oh wow, 81? What the F? It's lighting up red, you see that? 81, 82 volts. Yeah, maybe this diode is better, or maybe the other diode is broken. Either way, that's awesome. 82 volts now. See if I can, I'm gonna move the camera instead because I don't want to disturb the system. But again, that's measuring it before the diode here. We got it just measured on just the output before the diode. And the diode comes in right here. So let's take another measurement after the diode again. It's weird. I don't understand it. So Steven says twist on the grip pattern with hockey tape and shrink wrap it. Get the wrap with hot glue liner. You can use Kerr's grind cat litter glued to the handle before heat wrapping. Works good on the big sledgehammers when you need to use the haymaker swing on a 1/4-inch pin. All right. So we're still 81 volts. Let's take another measurement. Let's move the probe. And move it to after the diode. I have a feeling it might just be one of these jumper cables that's just kind of shitty. We'll see in a minute. We'll see. Yeah, 0.0, 0.02, 0.05. It's going up and down, but that's weird.
No. It is a problem with the jumper cables, I think. All right. Hold on. Let's take one more measurement just to be sure. Let's see. Take that here. Probe. No, it's not the jumper cables. We're getting 78 volts before the diode. I don't understand. I'm completely dumbfounded. I'm gonna have to contemplate on this and do some research to understand what this exactly means, or I have to mess with it a little bit tonight as well. So I'm not gonna end the stream right now. We'll do some more testing. No, you're good, Steven. You're good. You guys are brainstorming over here, and so am I. I'm just like kind of stuck because the readings I'm getting that are high voltage are before the diode, but the diode needs to be attached unless I don't understand it. The diode is providing impedance, so part of wave bounces back. Oh, so what do you suggest, Elijah? Like at this point, I'm getting high voltage, but how do I get that into something usable? I know it's something simple, like something stupid simple, like maybe attach a resistor to it or something. I don't know. Oh man, I could also try messing with it while it's in tune as well, because remember, it was getting 48 volts versus 60. When it was in tune, it was still getting 48 volts. So I can try that as well. This is interesting. Oh, this went down. Oh, this got disconnected. Okay, that's why. So the jumper cables are good. Oh. 67. 35 milliamp draw on the battery. Use a transformer. I could try the like just a single channel of the paradox box, the north to north magnet bifilar coil that acts as a transformer. I could try that. Let me grab that real quick. Let me grab the paradox box. See if we can do something with that.
So on secondary winding, red wire, put 2 diodes. Secondary winding of the transformer or of my coil, my ABHA coil? Red wire, put 2 diodes, half bridge for relative ground. So with those two, half bridge, those 2 diodes would be in series. Would they be like facing each other, like the anode and cathode would be touching? Oh, of the transformer. On the secondary winding, okay, red wire, put 2 diodes. We're gonna have to get the breadboard here. So that's our rectifier. We have 2 full bridge rectifiers on the board right now. You're saying I just need 2 diodes. And which configuration should I put them in though? Facing each other, facing the same way, towards the transformer, away from the transformer. Okay, so on the pickup channel of the transformer, we're going to put 2 diodes that are opposite direction at the end of the wire. Okay. So, are they each going to be pointing outwards or pointing inwards, though? The energy flow. I'm assuming they're both going to be pointing inward. I don't think it would block it if it was pointing outward. So I'm assuming you mean point them inward. So we're going to try this. I'm just going to attach that to the power rail of the breadboard. Just like that. Maybe he means the diodes facing the same direction. No, he said opposite directions at the end of the wire. So I just need to determine if they're going to be facing outward or facing inward. So we're going to just try hooking up the transformer, the paradox box, just by itself before we mess with any diodes, just to see how it reacts to the system. I'm going to put the paradox box after the diode, in between the end of the diode and the load. So it's going to be just after the diode, just before the light bulb. You shut up. I know. Let me turn that off for a minute. So right now I'm going to utilize a induction method of configuring a transformer, which is hooking up the start and end of one channel to the positive and negative between the load, and then the start and end of the second channel will be the pickup. So it's basically going to be like a bridge in the coil from one channel to the other, connecting one side to the other through each channel. So we are almost done with the connection right now. Just got to hook up the second channel to the light bulb. Grab some more alligator clips. So the paradox box is hooked up. I don't see any kind of noticeable difference. It seemed to reduce the voltage to 57. And the light bulb isn't lit. Yeah, so we have the system hooked up. It's registering voltage. It's just registering less voltage. Everything is hooked up right. it went down to 57 and it was at like 70 volts. So that's interesting. But it is working. It's picking up voltage. Let me try moving the probe, because this is registering before the transformer. Let me move the probe to after the transformer to see what's coming out of the transformer. Okay, so there's nothing coming out of the transformer right now. So either we have it hooked up wrong, which I don't think we do, or it's just not doing anything because maybe we don't have the diodes, like Elijah said. I'll when I go back to the workstation in a minute, we'll take a look at the video that Elijah sent, and maybe we can brainstorm and see if we can, brainstorm a couple of new tests to run. And I'll determine if maybe I feel up to running those tonight or not. But let me try a couple more things here before we go back and head over to the workstation and start that video and brainstorming process. Phone almost dead, still at hospital. If I'm MIA, that's why. I'm sorry to hear that you're at the hospital, Elijah. Definitely don't make this a priority if that's the case. We can always pick this up at a later time. Hey, what's going on, society? Good to have you here. We are just testing the paradox box and resonance relay extension wire on the Lightning Thief device. And we're having some mixed results. We got the voltage up to, what was it, 82 volts, guys? Coming out as free energy being picked up from the pickup coil. You see the Christmas coil here at the bottom. Here, I'll adjust the camera so you guys can see a little better. This tripod kind of droops. So let's put that there so you guys can see it. So this is the Christmas coil. It's now hooked up to the battery, guys. That's picking up energy being induced wirelessly from coil to coil. Kind of like a Tesla coil, only without the dangerous plasma discharge associated with those. So this is a more safe wireless induction technology that is actually way more efficient than anything that we see with phones. You know, your wireless induction pad, for instance. I'm using one right now to charge my phone. Way more efficient, and the distance that you can charge these suckers is increased tenfold. So I've seen a big radius of energy being able to be tapped off of the primary coil, quite a bit of usable energy. And this with this dual thief setup with the two lightning thieves I have, one lightning thief on the primary hooked up to the source battery, and the secondary not hooked up to anything but the secondary coil that's just picking up all that extra energy sitting on top of it. It's it's a very interesting system because we see high voltage coming out of there with this neon. Here, I can actually probably disconnect this and show you guys. It should still work. The system didn't break. Yep, see. Get a zoom shot of that. So when it's tuned, this is picking up free energy. That's high voltage right there. And it's not affecting the lighting at all. Not affecting the lighting at all. See? Turn it on. It's on right now. Didn't affect anything. Turn it off. It doesn't do shit. It's free energy being picked up because it's it's utilizing that captured. It's capturing and utilizing that back EMF and recycling it. And, maybe, I don't know exactly how the wireless induction works at the moment, but I have a feeling maybe it is, I hypothesize maybe it's, creating a collapsing field itself, and it's because that makes sense. The Joule Thief is designed to utilize that back EMF. So, and you'll never see another system like this with the Joule Thief. Okay, this is the first time I've ever seen what I'm doing here, using one Joule Thief to wirelessly induce energy into another Joule Thief, being picked up and amplifying that wireless energy. I've never seen anybody do this before. So this is pretty groundbreaking stuff that we're doing, and if we can utilize some of this extra picked up energy and direct it back into the battery, we really have something here, because this is just practical, tangible evidence that you can recycle energy in systems and close the loop. I mean, this is like the first step here is picking up extra energy, and now we have to decide how we're going to dump it back into the source. But that's I mean, we got 80 volts, guys. If we can convert some of those volts into current, and get at least 12, 13 volts, easy. So we should be able to do this if we put our heads together. Because I'm really stuck right now on how to proceed with this. Let me just show you the lumen lamp too while I'm at it. So that's the lumen lamp. Everything is open source. You can get the plans for the lumen lamp right now online via Michelle's YouTube channel or mine. But we will be making them to sell for people who don't have the capabilities of making them themselves. We are going to be selling kits for those and pre-assembled units as well. So for people who don't really want to build it, or for people who want to build it, like a do-it-yourself kit, tinkers, like can give you the parts and you just build it yourself. It's a fun kit. I'm not gonna lie, it's not very hard to put it together. Some parts are a little tedious, but we're working on making a more convenient frame for the lumen lamp. And it does have, again, it does have swappable coils. So that coil in the back that you see is swappable. That's a fusion coil. We also have the caduceus coil and others in development. So, and I've also hooked up my micro vortex coil to this baby as well. The lumen lamp works with the micro vortex coil. It needs some minor tweaks with the resistance. That's all. But I did get it to light up the light bulb momentarily. So, that was pretty cool, because before then I didn't know if the micro vortex coil even worked. I had just got done finishing soldering the connections and finishing the coil. I never really got to test it. So society says, if you powered this with a capacitor bank with a known drain time per load, you could calculate if the system was gaining power, because it would increase the time discharge of the capacitor. That is cool. Yes, society, please email me, and we have to get together, and you must walk me through this process, because this is very vital to the research I'm doing. We need to determine the efficiency and determine if there is any power gain, because it's very tricky to do. It's very tricky to do. There's a lot of different variables. And even if, like we've seen, even if we're picking up that the coil is maintaining current while stepping up voltage, in some instances we see that the system itself is losing like a ton of current when it shouldn't be. So, all that stuff is, it obfuscates what we're seeing here in terms of efficiency. And I think if we have like a simple process like you described with the capacitor bank, because I do have Ian's cap bank. I'll show you right now. It's all these capacitors in parallel. I don't know if that will work, but let me know. I'll grab it right now. right, so that's Ian's cap bank. Again, email me, Society. I'll put my email in the chat if you don't have it, but you need to help me help walk me through this process, because I have absolutely no idea what this process is of calculating the drain time per load with the cap bank. So if you could help me with that process, I think we can calculate the efficiency of the system maybe finally. Because again, like we're getting all sorts of calculations, but they're approximates, and there's all sorts of variables to consider that kind of obfuscate the actual efficiency of the system. So you just hook your load to the cap bank and time how long it takes for it to drain, and then do it again with the joule thief. Oh. Take your load, attach it to a cap bank. Okay. So I'm wondering how we would set up the control here. Would we use the inverter? So I have this inverter that I've been using. Here. I have this DC to AC inverter that we've been using for the 12-volt battery to test against the control, which it lights the 40-watt bulb, but it lights it at 100% brightness or near it or whatever. And yeah, it only lights it for 10 minutes, by the way. Like it drains it for 10 minutes when the same time this system like goes for like what, hours, 15 hours or something like that. So I'm wondering if I can use this as the control here, and we can attach the cap bank with the inverter. But then again, with the brightness, because it's drawing 37 watts, it's a lot more. With the brightness in the watt consumption of the inverter compared to the joule thief system, would that affect the capacitor's draw? I'm sorry, the capacitor's discharge rate. That's what I'm wondering. Could we actually use this as a control, or is it going to not be an apples to apples comparison? I think we could do that with the inverter now that I'm thinking about it, because it's just powering a capacitor, and then we're testing how long that capacitor takes to discharge. I don't think the amount of power consumption from the battery necessarily would affect that decay rate of the capacitor. So yeah, maybe we'll set that up for tomorrow for our pre-game show. Maybe we'll have a special interactive lab for our Free Energy Fridays pre-game show tomorrow, and we'll test out a couple of these ideas. Right now, I'm gonna go back to the workstation, and we're going to do a quick intermission while I get set up at the workstation and go over some of these ideas so I can write them down and schedule them for tomorrow's pregame show. All right. Welcome back, ladies and gentlemen. So, we had some mixed results there. Let's go over some of the ideas that some of our team members from chat have had for us. Let's see. So, we had some mixed results, but as I stated earlier, by switching the resonance relay to a different resonance relay, I made a bunch of them. They're the same diode. It's weird. By just switching the resonance relay to a different one, we increased our voltage to 82 volts, and it actually gave us the warning indicator on our multimeter, which was really cool. Normally I don't like to see that indicator, but in this instance that was really really cool to see such high voltage coming out I was not expecting that. So we had a couple of suggestions because we didn't really get any results with the transformer or switching the diode there. Didn't really do much. So we had a suggestion from chat regarding a wireless receiver from new member TenorSax999. So thank you, TenorSax, for your suggestion. That is a great idea. We will look into utilizing wireless receivers for picking up some of that energy. We have a diode arrangement with a transformer recommended by Elijah Tack. Now, we tried the transformer without the diode arrangement. I haven't seen the video that he sent us, so we're going to take a look at that video. And we also have a cap bank drain test idea from Society of High Sciences. And much appreciated, guys. This is some really good information to get started with our next line of tests. Specifically, this cap bank idea for testing the Joule Thief efficiency. So let me read exactly what Society had to say, because he said it beautifully, and I don't want to mesh up his words or mince his words. So he said, you know, if you power this with a capacitor bank with a known drain time per load, you can calculate the system if the system was gaining power, because it would increase the time discharge for the capacitors. So this is a brilliant idea, and this is something we need. A simple idea, something stupidly simple that we could test the efficiency to eliminate all these obfuscating and frustrating variables that kind of make it difficult to gauge the efficiency of the system. We want to just see if it's getting any kind of extra energy, right? Any energy gain. And this could be what we need to calculate that. So we're going to put that on the list for sure, and I'm going to be in communication with Society about exactly how to utilize that test so that I don't screw it up. So let's take a look at that video that Elijah Tack sent. Oh, hey, it's Joel. Nice. All right. And that's when you're using the Tesla coil as a not as a pump, but something that outputs energy. So when you see the plasma discharge, That's a whole bunch of wasted energy. With the ABHA system, you're taking the benefits of the wireless induction from the Tesla coil and translating it into something that's more practical and usable for everyday use. And it's basically an extension of Tesla's work. If you want the true behind the curtains veil of the research behind the ABHA coil, it really is just an extension of Tesla's work, and it is described by Daniel and Erica Nunez, who invented the ABHA coil. It is described by them as a Tesla pancake coil in three-dimensional toroidal winding pattern. So it's nothing new. You know, it's just an extension of what Tesla was doing, and yeah, we can get definitely some interesting effects out of the coil, but also it seems to be able to handle energy very well and resonance very well. So with the lightning thief system, we see enormous amounts of efficiency, but it's hard to gauge it. So we're trying to gauge exactly what kind of efficiency we're having in the system right now. And you know, metrology is very hard from what I've had to learn, unfortunately, in the last few weeks. Oh yes, let me turn the subtitles on.
So this is just going to be a trigger. So we're going to say a very small inverter, 25 watts. And we'll say it's high frequency for convenience. We'll say 400 hertz. And the output of here is going to be AC. We'll say 200 volts. So now traditionally what everyone wants to do is close the loop here. Let's not do this, because right now the only thing we're paying for is running the inverter as a free running oscillator. Very similar to when you plug in a transformer on the...
So this is he's describing exactly what is going on in my system, where we're getting like 80 volts coming out, but that's like without, you know, like we're getting the voltage that we need without anything attached, basically. We're picking that up right at the output of the lightning thief. I'm curious why yeah, I'm curious why the light bulb, I know it acts as a capacitor, but why it increases the voltage. That's very interesting. To like 80, I think we got on the meter. If we can do that while keeping that open end, he's saying maybe we can utilize that potential.
The wall, and you're not running anything on the end, you're still paying for the magnetization and the stray losses of the transformer. Here in our case, because we're using a battery, it's the actual inverter. Now, one's for the cars and 60 hertz, those could take 5 watts or more. It is the way it is. The inverter will always take a certain amount, but it may not be very much.
Yeah, it's going to utilize some of that energy to just use the inverter. We don't use an inverter. We use the Joule Thief circuit, which doesn't seem to be wasting any energy with the 0.6 watt load. It's taking in 10 milliamps from the battery and putting out 10 milliamps to the load while stepping up the voltage. It's flipping crazy. It's crazy, guys. It's crazy. I don't understand it.
It's not being loaded. Now, according to our laws of physics, the Lenz's law specifically, in order to load this, we need to close the loop here.
You know what? I think Elijah might be onto something. He said adding the light bulb might be adding a bell ringing effect, and it is. It's singing, it's humming when the light bulb's attached, and then you disconnect. But that's when the coil is saturated. Then you disconnect the negative load once it's saturated and humming, and it increases the efficiency. That's when everything stables out. Really, is when you disconnect the negative load after it starts humming. So it has the bell ringing effect, and you disconnect the load because, yeah, like Elijah said, maybe it's ringing the bell and you're saturating the coil, but you don't need to keep on ringing the bell over and over and over again. You're just whacking it over and over again. Kind of like Jarvis was talking about. You just need to whack the bell once and then disconnect the load, and then it just resonates. It saturates the coil, and then the coil, once it's saturated, it seems to discharge its energy very slowly and stabilize with the system, the requirements of the system. So it'll last like days and days, it seems, discharging it at that slow rate. So a very, very unique system. You'll never see anything else like it. And we're trying to work out the kinks so that you guys can utilize this. Hopefully by the end of this year. Hopefully we'll get some on the market by the end of this year. And they're not going to be too expensive. Maybe 30, 40 bucks. I haven't calculated the exact cost, but it's going to be cheap for these Lightning Thief devices. They're going to have to be, maybe a little bit more in the first round of them, but they're not going to be too expensive, So that's pretty cool. Pretty cool off-the-grid system. I will be selling the coils as well for anybody who wants coils. I just had somebody pop in earlier offering assistance with putting together these kits, and that was very generous. We will be needing all the help we can get in starting the Coil Kits Lab shop, which will be providing some of these energy solutions to you guys. You'll be able to go on to Coil Kits Lab shop and build your kit, your coil kit. Pick your coil, pick your device. We have a host of devices that we have planned. The Lightning Thief is the energy efficient lighting and potentially heating system. And we also have a pulse motor called the Green Machine, which utilizes an open circuit method of pulsing the coil. And when done correctly, this can bring down, we've got a neodymium sphere to spin, simulating a magnetic rotary, because I don't have a magnetic rotary, but we got it to spin at such a high RPM that it lowered the input wattage requirement for the entire system by 30 watts. I'll say that again. Our Green Machine pulse motor system was able to spin a neodymium sphere so fast that on the wattmin that we had on the wall for the entire system plugged into it, it was requiring like 42 or 45 watts, I think, something like that, 45 watts. And then once we started spinning the sphere and got it tuned in enough and spinning fast enough, we got that reduced 30 watts to like 12 or 15 watts, something like that, on the input requirement for the wall wattmin. It was a phenomenal moment. I'll find the video for you guys in a minute, but I just want to say, like, when you go into Coil Kits Lab Shop, these are the types of things that you'll be having access to in terms of options for your kits. The Green Machine is a phenomenal system, and part of the research that I'm doing, trying to close the loop with the Lightning Thief, is going to be able to play into how we utilize some of that energy, because that's been a problem. You got all this reduction of energy, and it's able to induce wirelessly from coil to coil quite efficiently, free energy, but we can't seem to be able to utilize the Green Machine's efficiency for anything practical at the moment, except for maybe spinning a magnetic rotary with a generator or something. But the most efficient, in my opinion, it seems like the most efficient utilization of the Green Machine and the Lightning Thief will be the wireless induction. So you'll be able to combine the Green Machine with a Lightning Thief. We have different combinations and connections that I've been working with called the Green Thief. That's connecting a Lightning Thief with the Green Machine. potentially what we're doing with the Dual Thief and picking up some of that wireless energy and utilizing it for something, putting it into something. We're saving energy. Why not use it for something? So not just, drawing less off the wall. That's cool, but, what are we going to use that for practically? So we have a whole bunch of options for you for starting off the Coil Kits Lab Shop, and it's going to be fun. It's going to be a fun experiment to see how many people are interested in these coils and not only experimenting with them, but utilizing them for maybe camping or, off the grid purposes. Say your power goes out and you need, like me, you just want to power your living room with some basic low wattage lighting on a 12-volt battery. You have an easy solution with that. So let's continue to see what Joel has to say, and then I'm going to try to load up that video for you guys to show you the Wattman reduction, because that's a really cool video. It's one of my favorites.
And when we close the loop, we create a load here, which creates a counter force, which shows up as current, which gets drawn in here. Now we don't want to do this, so let's not do that. So we're going to delete our loop here. And we'll say this is, you can pick any wire, we're going to pick this one here. And we're going to do our one wire system here. So I'm going to put the 2 diodes on the 1 wire. So I'm not a good drawer, I'm sorry about that. So there's 1 diode here. And there's another one there. This, and then over here would be our DC pulse at this point, because we don't have a capacitor, but this would give us, it won't be very much because this is just 200 volts, so it's not really optimized this way, but I'm just trying to explain it, is you may get a volt or two like this. So we need to take it an extra step.
Hold on, how did he draw those diodes?
But I'm just trying. Over here with the system here, so I'm going to put the 2 diodes on the 1 wire. So I'm not a good drawer, I'm sorry about that. So there's 1 diode here, and there's another one there, like this, and then over here would be our DC.
So the negative diode is for the energy facing where the negative energy is normally going, okay. And then the positive diodes forcing the energy to the positive. Okay, so it's basically just, okay, directing the normal energy flow. It's not doing anything abnormal. I think I understand.
DC pulse at this point because we don't have a capacitor, but this would give us, it won't be very much because this is just 200 volts, so it's not really optimized this way, but I'm just trying to explain it, is you may get a volt or two like this. So we need to take it an extra step. So let's run the microwave transformer on this. So here's our microwave transformer right here. And here's our primary side, and here's a secondary side. So what we're going to do is we're going to feed into the low voltage primary. So we'll say our 200 volts goes here. Now you see what happens here is we're energizing the primary, but because at this point here, we've got nothing on our secondary here, the core is live, so here's live core. So what happens here again, it's just magnetization. You're paying for very, very minimal loss here.
The Ben thief. So yeah, he's absolutely onto something if he recommended the Joule Thief to you, because it's a magnificent circuit to people who understand its real capabilities, and people who've worked with it with an open, free energy oriented mind really see the potential in the Joule Thief, and like Gerald, you could ask Gerald. He knows all about the Joule Thief. He's worked with it. He's working with a modified version of it now that utilizes 2 transistors. I called it a dual thief for a while, and then I discovered the wireless pickup method from coil to coil utilizing 2 Joule thieves for my system, and then I coined the term dual thief for that connection setup, because that kind of like encapsulates the connection setup and simplifies it for everybody, because we have a different connections. We have the dual thief, we have the thruple thief, which is utilizing 2 Joule thief circuits in 1 pickup coil, and then a primary, which is really cool because both of them pick up high voltage and excite a neon. That's very exciting. We'll probably be working more with that in the near future once I get some more boards soldered together. Yeah, so we have a whole host of different kinds of connections that we can do. We have the paradox thief, where we can hook up the paradox box to the Joule thief circuit, so all sorts of cool stuff. We also have a piezoelectric transducer we can do something with. Lots of different stuff to work with. I'm sure we'll figure something out in terms of how to recycle this energy and dump it back into the source. For now, let's look at the... I want to show you guys the Wattman reduction video. It's one of the most celebrated, one of my most celebrated moments, because this is just clear, undebatable efficiency gains on an extremely abundant level. So, and again, we did get this to go down 30 watts. You're not going to see it go down 30 watts here, but it's a demonstration of how it's reducing. We got this to go down 30 watts live on stream while I was doing one of my live demo labs. So that was really exciting. Like, I think that was the one where I like kind of like yelled and screamed like a little schoolgirl. I was so excited. It was so cool. But look at this. Okay, so we have 10 volts. That's my power source, my power supply. We have 10 volts going in, and the current will change because we're you know, spinning a neodymium sphere in the system. So at the start, I think I had to turn off the system because it was still kind of wonky from me spinning it before.
All right, everybody, here's something really cool. We have the stereo method hooked up right now.
So this is going to be using the stereo method, which is going to be what's what the green machine is going to be. It's basically going to be a pulse motor system. We haven't actually finished the circuit for it yet, but it's still in the works.
Okay, 10 volts from our power supply at 140 milliamps. Okay, we're going to spin this little neodymium magnet and we're going to monitor the wattage. Okay, oh, it's not going to show it. Oh, you got to show it. There we go. Okay, so 7.3 because we don't have it on. We're going to turn it up. Check this out.
So we're turning up the mini stereo amp board.
Let me take that.
We'll show you it consumes more because we're turning up the volume.
We're going to turn it on.
Getting more
I'm turning it
into
up.
the system.
Look at the watt consumption. 24 watts. Okay.
This is absolutely insane.
Now watch this. We're going to put the neodymium magnet in there, spin it up, increase the frequency.
So there's a whole tuning method to do this, and I've went over it in previous live streams, and I might do it again at some point in the near future just for you guys as a refresher, because there is a method to doing this.
Now check this out. Wow. And then it goes back up, 24. We saved 10 watts of power by spinning this thing. Holy crap.
Holy crap is right. If you haven't hit that like button, then go ahead and do it, because now's the time. This is extremely important research, ladies and gentlemen. And people should be paying more attention to what these coils are capable of. Unfortunately, we don't have a lot of attention on this channel at the moment, but we will. We will, because the science is warranted of the eyes of the scientific community. That is a 10-watt reduction. Remember, I just said we got a 30-watt reduction. I think it's because that volume knob wasn't turned all the way up. And it still went down to like 14 watts or whatever. 30-watt reduction, that's insane. That's phenomenal. Absolutely incredible. So the fact that nobody is talking about this in science is just disappointing, and that needs to be corrected. So anybody who is interested in this stuff, I suggest please liking, subscribing, sharing this channel to anybody who is interested in getting started with some of this new science that's going on. So this is a very exciting time, very exciting time. We have some really cool stuff going on with these coils. Let's see what's going on in chat. You know what? There might be a couple more videos I want to show you guys. Give me 1 second. So here you see the early version of the green machine at the bottom, with the big ass toggle switch with the shield. You flip it up. That's not gonna be. That's just something I added for fun. That's, you know, it's just a prototype, an early version. It's not even printed green because I didn't have green plastic at the time. So, but this is kind of what it's gonna look like. It might be a little bit bigger than that because we're actually gonna try to fit the micro vortex coil inside this device, so it's kind of like an all-in-one inclusive system. That would be really cool if I can get that done. That's the goal of the green machine. It's still in development. I mean, the technology behind it is going to work, but whether we can you know, develop some kind of easy all-in-one consumer version within the time frame that I want is another thing entirely. So that's the idea of the green machine. Is going to have an LCD display for efficiency monitoring. So what we're going to have, or what we want to have for the system, is we want to have an LCD screen with a menu system that will give you different options. Specifically, you want to be able to monitor the input and output current and voltage, right? So it's going to act as a wattman for the input and output of the system. So you can easily gauge the efficiency right on the LCD screen. We also want to have a, you know, different host of options, like maybe a timer system, so you can, you know, if you're timing how long a battery takes to drain, you can have that and organized right in the menu. Also, we want to have a sensor in the system to pick up the RPM. So if we can pick up the pulse rate, we can pick up kind of like the RPM of the system. That would be pretty cool, and you can have the RPM on the monitor right there. We have different options. That's still in development. What we know for a fact works and is going to have a consumer version ready either by the end of this year or early first quarter next year is the Lightning Thief device on the top here. You see in the middle between the coil and the green machine. So the Lightning Thief is going to look a little bit different than this. It's going to actually, the consumer version is going to utilize proper connections. So it's not going to have these stupid jumper cables. That's just for the prototyping, for convenience, for testing and stuff like that. But the consumer version will have 2 1/8-inch auxiliary cables, one for each channel of the coil. So that will be your coil input. So basically two headphone jacks for the coil input, and then we'll have a simple DC jack for the power with adapter options for batteries and stuff like that. And we will also be utilizing 2 USB, I think we're going to do USB 3.0, maybe 2.0, we'll see, but 2 USB outputs for each load. So we have 2 load outputs for the Lightning Thief device, one for each circuit. There's 2 circuits built into the PCB. There's the open circuit method and the closed circuit method. So we have a couple options to test with for you guys, and there will be a toggle switch to toggle between those. You'll be able to utilize one at a time, obviously. So there will be two different outputs for the load, and we want that to be easy to adapt to different, situations. So I'm thinking maybe a USB type plug would be the easiest and more convenient option. So that's what I have planned for the Lightning Thief. It's going to be awesome. Oh, it will also be utilizing two banana plugs at the bottom, which do work. I've tested it out. The banana plugs are for the potentiometer. So the potentiometer is for tuning. That's going to be at the top. You've seen me use it in the live stream lab demos earlier. You twist it to adjust the resistance and tune it. Basically, that's how you tune your system. So if you want to go in, and since the Lightning Thief is going to be made so it's easily modifiable, easily upgradable, nothing's going to be soldered really on the board. Everything will have terminals, screw terminals. So you'll be able to, I don't know, swap a transistor out if you want to try a different transistor, or adjust the resistance to your system specifically. So if your coil is a lot smaller, like the micro vortex coil, you'll have to adjust the resistance. But either way, you have the banana plug option in there. So once you tune your system and get that neon light to excite and glow, you have the option to plug in your banana plugs and unplug the system. You have to unplug it from the battery and everything, and then measure the ohms of resistance. So once you have that, you can go in and open the device up and just replace the potentiometer with a resistor, and your system is always in tune. So if you just don't want to if you want the system to run in tune constantly, if you're saying you want to run it for lighting or something in your office, and you're not worried about detuning it, or you don't care about standby mode, or standby mode isn't for you, or it's not an option that will work with your specific type of light bulb, you can go in there, easy, 4 screws, and just put your resistor in there, and it'll easily allow you to do that. Measure the resistance of your system and replace it with a resistor very easily. And again, if you burn something out, the PCB has swappable components. So I don't want you guys to have to buy another Lightning Thief device if you burn out your transistor, which might happen, right? You might burn out the transistor. It happens sometimes. Sometimes the neon isn't, connected properly, or, you drop the device and it gets disconnected a little bit. Whatever the case may be, whatever option or whatever variable to consider. If you fry something out, you can easily go in there and replace a component instead of having to buy a whole new device. So that's the idea of the Lightning Thief. We don't want to, I'm not trying to sell you guys 1,000 units, I want you guys to have one each, or maybe 2 if you want to utilize the dual thief setup. But the idea is to have an easy, low-cost lighting solution for off-the-grid applications, and that's basically what this does, and what I've been using it for specifically in my own personal apartment setting. So it's pretty cool. Let me go and show you real quick. This is the micro vortex coil. So this is the coil that I kind of want to try to fit into the Green Machine pulse motor system, to be kind of like an all-in-one system. I thought this let me try to zoom in a little bit. Yeah, so I thought this coil was awesome. It was kind of difficult to wind, but it didn't take me too long to wind, fortunately. I forget how many wires it's using. Oh, it's using 12. So instead of the standard 24 bundle of wires, we're only using 12. But 12 is what Daniel Nunez specifically said is the minimum threshold to utilize some of this 0 point energy coming out of the coil. It's some kind of threshold effect where, I guess you don't see a lot of usable energy unless you have 12 wires in the bundle. For some reason, that's the threshold of the magnetic fields compressing on top of each other to produce this kind of effect. So lots of cool stuff. think I wanted to show you another video. Let me see if I can find it. Give me 1 second. I'm gonna... There we go. That's cool. You guys can see that. Where is that? Screenshots. Nice. So this is the actual current prototype of the green machine. I don't have it programmed yet. I tried to program a menu system into it, a rudimentary menu system with a timer circuit or timer program on her, but for some reason I can't get it to display anything currently. You know, my programming skills are weak, so I'm using Chat GPT to help with that. So that's still in development though, but that's what it's going to look like. It's going to be green like that, and it's going to be maybe a little bit bigger because we got to fit the vortex coil in there. So, but it'll have maybe 4 push buttons on either side, or 2 on either side of the LCD screen at the top, as you can see. And then the power switch, the toggle switch, will be at the bottom where that little hole is. Okay, so we have the lumen lamp with the resonance relay and Charmander transistor. I'm going to put that up there because that's a nice one. It's in the dual thief. So this is the lumen lamp, and I attached the resonance relay to it, which is just the diode suggested by Michel in placement in the placement of on the positive rail of the load, just to try to capture some of that back EMF and redirect it. So it's working really well, and I have it working with the MJE 13009 transistor, which I've been labeling Charmander because I don't like to say that, it's long. And Michel has been working with Squirtle, which is the MJ21194G. Yes. So as you can see, I don't like saying those, so I just codenamed them Squirtle and Charmander. So I'm using the Charmander transistor here, which is absolute fire. It is a cool transistor. It's what I've been using for the Lightning Thief. Seems to squeeze energy like no other. Let's take a look at that one more time. And it lights it a lot brighter. Like I'm talking significantly brighter. the other transistor at the same kind of like setting on the potentiometer. So, or either that, or it could be, it's probably adjusting the frequency, but at the same time, it does seem like it's utilizing the light more efficiently. Mike Does says, when the drive coil is not receiving power from the supply, it is available to receive from the sphere mag. Remember, it's a DC pulse system on off. Yeah, that's true. That's absolutely true, Mike. I didn't think about it that way. When it's off, it is able to receive. So wow. No, that's a good way of thinking about it. Thank you. Thank you, Mike Does. So this is Mike Does, and he really knows his stuff. He knows his stuff so much that I made a song about it. Regardless, Mike Does knows we're his biggest fans. No, so yeah, we're not using any kind of inverter. We're actually comparing the efficiency of my system with an inverter. And so far it's kicking the inverter's ass. Even though it's only lighting it about, it appears to be lighting it only at about 1% brightness. Like maybe 1 or 2% brightness, which is still pretty bright for a 40 watt, shop light that's supposed to light, a big area. It's lasting, 48, 60 hours, something like that, compared to the inverter, which lights it, near 100% brightness, only 10 minutes. 10 minutes. So that's the kind of efficiency we're dealing with. It's just frustrating because we can't see if we're actually getting gains or we're getting losses, and it's hard to gauge what exactly is going on. Oh, but the stereo is AC. Yes, the stereo is AC. Let's put this up here. Where'd my video go? Let's see if I can find that video. Here we go. All right. Load this one up. It's under... Okay, here's the MJ21194 transistor at 400 milliamps, or approximately what the other limit was. We'll compare brightness and decay rate. Okay, here's the MJ21194 transistor at 400 milliamps, or approximately what the other limit was. We'll compare brightness and decay rate. Okay, so this is 400 milliamps with the 13009 transistor. Hear how louder it is, the sound? I don't know, it looks slightly more brighter. It's definitely brighter.
The dial can go up to 3 o'clock or a little bit past 3 o'clock, whereas before it would turn on around 6 o'clock here, and the 400 would be around somewhere the 9 o'clock. So for the equivalent here, we'd be around 9 o'clock, and this is around 3 o'clock for this 13009 transistor. I don't know, we're gonna compare the light. Might be a little brighter, we'll see. Also, something that's weird here, I don't know if this means anything, Michelle, but I'm detuning it. The light's turning off, but this neon is not turning off no matter what setting. And it's changing, the potentiometer's changing. What is going on here? That's never happened like that. Oh, and I got the dual thief set up, so with a large bit of help from Michelle Morel, my entire lab is powered by radiant energy now. At least the lighting. The banana plug concept should be more like this. I don't think I'm going to keep these big connectors. I think I'm just going to shave off and keep it at the bottom all sleek like this. And just plug it in right here.
Banana, ooh la la.
And this other end will be your multimeter. Wanted to get this on camera before I fuck it up again. But here's the toggle switch. Oh, of course the AC or the heat kicks on when I'm recording. Okay, so here's the toggle switch. Ooh, and that's the closed circuit method, baby. Ooh, baby. All right, let's turn that off.
So that's the Frankenstein version of the board. I have
As you can
since put
see,
together more
everything on the
clean
board
versions with
now
screw terminal.
is swappable. This is just a very rough draft, a very rough
Actually, let me go show you guys
cut of the prototype. Everything will be more neatly organized with professional proper terminals. So we'll have the proper terminals, female jacks input into here instead of these makeshift female jumper cables from the Arduino kit I have. I have the resonance of this Mark I coil already, so I ran out of potentiometers, the 1 mega ohms, so I just went ahead and put the resistor there, so we don't have the ability to actually tune it right now. But when I get another pot, I can just easily swap that out. So that just unplugs, and like everything, this is the diode,
if you're out of
this
pot,
is the
guys,
1K
if you're out
ohm
of pot,
resistor,
just use a
the
resistor.
transistor here swaps out. Everything's going to be able to be everything's going to be swappable on the prototype I'm going to send out to
But yeah,
the team.
as you can see, everything's
and the
swappable.
consumer version is going to be aimed at that as well. I don't really know what the consumer version is going to be like yet because we have testing to do to make sure that the configuration is configured properly and optimized properly. So at the end of the day, there could be changes that we make depending on what we see in our testing. But everything to this moment is swappable. You can see I have the 3-pin toggle switch to toggle between the open and closed circuit method here, which is right here. You can see the closed method and open method, and they're connected with this wire, this white wire, and the white wire is a Y junction that I soldered myself. So you have both connected to the common ground, and then either gets the positive for their respective circuits. So you can toggle between them, see? All right.
So this is the PCB board that will be shipping with the Lightning Thief device. It is utilizing two methods, an open circuit method at the top and a closed circuit method at the bottom. You can see everything is easily swappable with these screw terminals here. It's just very convenient. It's upgradable, modifiable. If you damage something like a component, you can easily swap it out. Very convenient for tinkerers who want to, experiment or tinker or, develop their own kind of system, modify it to their own requirements. Very cool stuff. Very cool indeed. And it works. I mean, I've been using it, so I just have to replicate it. And unfortunately, the 3D printer I have it is on the fritz. It's giving me a temperature, a thermal halt error or something for the bed. Thermal sensor or something, so I have to figure that out before I can print more. But I do have, I think at least 3 or 4 good cases that I can put together, maybe start putting together something for a few members of the team while I sort the 3D printer situation out. Society of High Sciences, can we see the draw on the power when the ball is spinning up? Yeah, so that's exactly, I'll pull it up again, but it was 14 watts. Method hooked up right now. I'm not gonna show it. We're gonna turn it on. So when the system is on without the neodymium spinning up, it's 24 watt consumption off of the wall. Now watch this. And it starts spinning up, and watch. We're gonna put the neodymium magnet in there, spin it up, increase the frequency. Check this out. Wow. 14. And again, that's consistent. Like, I can turn up the power a lot more and it'll always go down to 14 or about that level. And we've gotten that reduction up to 30 watts, reduced from, I think it was like 44 or something like that. So when you turn the volume all the way up, it's consuming 44 watts because, again, it is a 40 watt board. That's what it's supposed to do. It's a mini board that pulls 40 watts per channel. I think, are we only using one channel? No, we're using both channels, but still it's only pulling 40 watts when you turn it all the way up. So, it's not unusual that the board is using 40 watts. What's unusual is that once it is using 40 watts, you start spinning the sphere, and then it reduces down to 14. So I think that's really cool. It's really extraordinary. It's really, really extraordinary stuff. See if I have any videos to show you guys before I end the stream. Oh yeah, we did test the micro vortex rotary. It didn't really turn out too well though. Wonder if I'll play it for you guys. Okay, I wanted to share something very, very, very weird. We have the micro vortex coil without the interference pattern. These are soldered, so everything is good to go. 17.9
Oh yeah,
volts
this is
going
without
into
the interference
18
pattern.
max volt board. Listen to it squeaking. What the F? Where is that coming? It's coming from the coil. It's still making the noise. I've never heard the system do that before. Just with this one, just with this coil. No, I didn't put oil in the glass yet, but that is a great idea. When I do that, I definitely have to remember my safety glasses and my hard hat. Listen to it squeaking. The little pipsqueak. It's so weird. These coils are so weird. In a good way, though. In a good way. I wonder if I have another video of that. So as you can see, without the interference pattern, it isn't as fast, but it's still stable and steady. Still spinning a lot faster than the one with the interference
RPMs
pattern.
with the tachyometer, and we get approximately
The one with the interference pattern wasn't spinning
anywhere
at the
from
sphere at all, but I think it's because it was really big. I
That's
don't
not
know.
right. Anywhere from 200 to 400 RPM. No, 582. That's what it was. This thing is a little crappy, but 582 is what it was registering at. That makes about sense visually. Got 9.3 and 2.33 amps in the wall. We go actually up from when we put the frequency in without the magnet. We go up from around 9.3, 10 watts to 30 watts. And with this, it might be going down slightly. I don't know. Let's take it out and see what it's at. So it's at 34.7, going down from 0.7 to 0.6. Let's take this out. Okay, yeah, so it was going down slightly, 34.7 to 34.6. Again, this thing without the interference pattern is significantly less efficient, but it still should serve its purpose for further testing. The weird thing about this is that you can actually hear the frequency without anything attached, with just the coil, and it's really weird. Really, I've never heard it with the other ones. Just making that noise. Yeah, you hear the high pitch with the lightning thief, but never with this setup have I heard it, except with the capacitor. So without the capacitor, this is interesting. So listen to this. Okay, hear the squeak. Listen for the squeaking. Little pip squeak. Okay, you hear the squeaking?
That's my pipsqueak coil.
That's the frequency. We're in square waves, so it's going to be squared and not sinusoidal. So, but listen to this. We take it out.
It's so cool. Well, the magnet's amplifying the sound, so
Still making that squeaking noise.
I just never heard it come from the coil itself. It's
Sounds like it's coming from the coil. Here comes the
At least
AC
not
to
in this
ruin our
configuration.
clip again. And notice we're going up and down on the current, okay? And I don't have anything attached, but it's still going up and down. Very weird.
That's the weird
with the
thing.
frequency.
Very
Interesting.
anomalous. Very, very strange occurrences happening in Coil Town. Which one is this? Oh, this is the 0.6 watt LED light bulb load for the Lightning Thief. Hear it singing? So I'm gonna start that again. Listen to it sing. It's literally singing to you when you plug it in. Coming from the light bulb itself. I've heard it come from the circuit many times, but never the light bulb. And in that other configuration, never the coil. I'm disconnecting the negative wire. And look at it stabilize. You see it stabilize? It was at like 70 something milliamps. And now it's going down to kind of like match the load's requirements. Pretty cool.
It stops making the noise.
And it stops making the noise.
It's only when this is making noise that the current seems to peak.
Pretty cool. Pretty cool. Yeah, very, very efficient system. See if I have another video to show you guys.
All right, we have the resonance relay, a new attachment that I'm going to be including with the prototypes and possibly the consumer version. I'm not sure on that yet. But this is basically a booster that captures and recycles some of the back EMF from the output power positive terminal. So here you see, this is the output of the load positive rail. And here's the extension that we have. It's called the resonance relay. It's got a small diode in there, and you can see that I have marked it with an arrow. I'll do a better job next time in making that arrow a little clearer. And that's going to the power rail. And this is about 48 to 50%, it seems, brightness. So that's very good.
Brighter,
Very good.
I
It went
meant.
from
I
like
meant to
5
say
to
about
10% bright. To about 50% bright with this boost relay, this
we didn't
resonance
have a
relay
lumen
here.
or a lux meter at that time. It's actually about 1% to 2% bright with the booster. Without the booster, it's half that. So, yeah, the lux meter, it's not an exact metric or an exact, it's not going to give us an exact amount of lumens that this thing is putting out. But maybe if maybe if I take the displacement screen off, we can get a little bit more of an accurate reading. I don't know. But at this time, it's reading it at least 1% brightness. From a 40 watt like LED panel that's quite bright at 100%. Honestly, it's way too bright for me. So it's actually a good thing that this system is kind of low. I'd like it to be maybe a little bit higher. I'd like to see maybe at least 5 to 10% brightness, but I don't need it to be 100%, 50%. I don't need it to be that bright. This is way too bright for a single bedroom apartment. This is a 40 watt panel meant for a huge, 2-3 car garage or a shop, so that's something to consider. Oh, Oh, so here I can show you some of the testing data that we did with the 40-watt panel, some of the graphs. Let's take a look at some of those. All right, so here we have the decay rate of the Lightning Thief system. And this is before the booster. This is before tuning it with disconnecting the negative load and adding 0.6 watt LED light bulbs for tuning purposes as capacitors. This is all before, you know, we had all this extra energy efficiency. This is already what we were getting with the system. So you would see that even though it was like maybe a 0.5% bright, you know, it still made a good night light. Like it honestly, it wasn't good enough for me to light in at night like this, like it is now. Now it makes a pretty decent, you know, low dimly lit night for the entire room. But at the time, this low brightness made a good night light, but it was still a little bit too low. But the decay rate on this, if you look, it's about 80 hours. So let's load the final image. This isn't the final. This is about 50 hours in. Oh, that's the wrong graph. I think I mislabeled this. Let me see. What is this? Oh, this is the inverter graph. Okay. So let's take a look at this though. So this is 100% bright. In comparison, actually, let me load both of those. Okay, so you can see the comparison between the inverter and the coil. Oh, there we go. Okay. Let's load the other image up real quick. That's the wrong image. Oh, I copied and pasted it, so it duplicated it. Hold on. Let me put a new one in there. Being difficult today, huh? All right, there it is. Let's move that one on top. All right, so let's compare these. We have both of the systems, both of the tests starting out at the same battery charge level, 12.4 volts or around there, 12.38, something like that. So we're starting out at the same point in the battery's charge capacity level. The inverter system on the left is charging, or is putting out not exactly 100% brightness, which is what it would be plugged into the wall, but probably closer to like 98, 99% bright, maybe a little lower than that. I don't know. I haven't exactly gotten a good measurement of it yet. So this system at 37 watts consumption from the battery, the 12 volt 20 amp hour battery, went down from the starting voltage, like 12.3 12.38 or 12.4 or something like that. It went down to the starting voltage to the end voltage in 10 minutes. That's actually supposed to be, this graph is wrong. This is supposed to be lower than this. This hit 12 at 10 minutes. So this graph is actually wrong. I don't know why. This must be the wrong graph. But either way, the inverter only lasted 10 minutes. So it's close. This graph's close, but no, it's actually lower than this. Because we stopped it at 12. We cut it off at 12, I believe. Let's see. What's the cutoff here? Yeah, 12. Yeah, so we cut it off at 12. And as you can see, it lasted like 25 hours, 24 hours. But it keeps on going. It keeps on going and going and going. And the projection rate is 80 hours for the system to reach 11 volts on the battery. And I've ran the system all the way down to 9 volts. So just comparison of systems, regardless if we're getting over unity or not, which I have a strong feeling that we are, we're just not utilizing it in a proper way. Regardless if we're getting over unity or not, this system is already extremely efficient, way more efficient than anything that you'll be able to find elsewhere, assuming that it's properly tuned. And that's the hard part here. We're trying to tune the capacitance of the system so that it's not screwing with the resonant frequency and the power output. So I have a bunch of different ways I make graphs. Sometimes I make them with Word document. Sometimes I make them with Chat GPT. And that graph I think was wrong. I don't know if I inputted the wrong data or it's a graph from something else, but that was the wrong graph. That measurement was supposed to be down to 0 at or down to 12 volts at 10 minutes. So the inverter only lasted 10 minutes on the battery. So that's very important. And what's frustrating is if we can only get the light to light up at the same brightness as the inverter, then we can definitively say, oh, this is more or less efficient, this is about the same efficiency, whatever. The fact that we can't get it to light as bright is the most frustrating element right now, because that's kind of obfuscating the efficiency of the system and making it really hard to tell what's going on. You know, we want to make sure like people understand if this is getting extra energy, we want to be able to easily measure it, right? We don't want it to be obfuscated in tons of variables that might make somebody question what's going on. This thing is highly efficient. It's just a damn shame that I can't determine exactly how efficient it is right now. But we're gonna run the CAP test, the CAP bank test that Society of High Sciences recommended. We do the CAP bank drain test. I'll be in contact with you, Society. We'll also maybe try the diode arrangement with the transformer that Elijah Tack suggested, and look into utilizing wireless receivers from the new member Tenor Sax 999. So I appreciate that, gentlemen, ladies or gentlemen. I don't know who you guys are, but I appreciate you guys. Anyways, I'm going to end the stream. I'm getting kind of tired here, and my voice is getting kind of hoarse from talking. So I appreciate you guys for tuning in. This was really awesome live stream. I had some really important updates to go over with you guys, and I was really excited to, give you guys those updates. So I will be uploading some more videos and some more clips to the channel Hey, Jessica. Yeah, talk to you later, Mike. I appreciate you guys for stopping by. Yeah, I'll be uploading some new videos to the channel, so I know I've been a bit behind on that, but at any rate, I appreciate you guys for tuning in, and catch you next time for tomorrow's Free Energy Friday. Free Energy Friday's pregame show. So yeah, we'll maybe be back in the lab for that. So I'll see you guys tomorrow.